structure which graphene has. So among this is, first of all, we have the linear dispersion at the K points, and the material itself does not have a band gap. So what I will show you in this talk is how we can construct actually molecular materials based on single molecules, which also can have interesting band structures, mainly show like topological features, like for example, the Dirac cones at the K point, or for example, flat bands in the example of the Kagome lattice. So using molecules gives us endless possibilities to create interesting lattices. And I choose here just 4 of them. They're way more interesting examples. If you want to have an overview of the band structure of different lattices, I refer to this review here. So if we start to construct now lattices of molecules with these structures, we have to think about several factors. So if we want to achieve nice electronic properties, first of all, we need to have a good pi conjugation among the molecules. So this means we cannot just take a self-assembly, because then the connection between the molecule is too weak to have a good electronic communication among the building blocks. So we need to use on-surface synthesis. So basically we switch from the self-assembly to the covalent bond formation, which we usually use functionalized molecules, for example, molecules with bromine end groups. And we use metallic surfaces most of the time, where we can like activate the molecules, for example, by heating or by light, and the molecules can connect in a covalent way together. So this is the step we have to do. We have to go from the self-assembly to the covalent bond formation. And the other more difficult aspect about this is we have to take care that we have a high crystallinity to actually really have long range order of these networks. So that seems to be very easy for the self-assemblies, because there we have a reversible bond formation. So basically, if you introduce a defect in your lattice, you can try to anneal it out, and therefore the self-assemblies are very long range ordered. This is slightly different for the covalent 2D networks, because the growth of porous covalent networks is mostly kinetically controlled. So if you're looking at this diagram here, so the thermodynamic stable product would be graphene, but it's exactly what we do not want. So we want to have like the open porous networks with a certain geometry, and they are usually kinetically controlled. So in order to achieve that, one has to either use some design rules, for example, to use like a hierarchical approach where one introduces a sequence of different reactions, or one has to use templates, for example, structured surfaces, or use self-assemblies as a template in order to get nicely ordered two-dimensional networks. A last point which we have to take into account if we create these covalent networks on surfaces is that actually if we put them on the surface, so these are calculations in gas phase, then usually the molecular networks feel an interaction with the surface, and then the bands start to shift up and down. So what we have to take care of is actually that the interesting features we are interested in, so for example, the crossing at the K point, that this is near the Fermi level. So to achieve that, we have most of the time to take care that we can electronically decouple the molecules from the substrate, because with the molecule surface interaction, we can heavily tune the arrangement of the bands in the band structure. Another thing which we could use as a concept is heteroatom doping. This also allows us basically to tune the electronic properties. So unfortunately, I cannot present you today a way how to decouple the covalent networks perfectly on a surface today, but I hope to show you points or examples to the first 2 points. So first, I start with the network which we could successfully synthesize on our surfaces, which is the gold surface, is like these triphenylamine networks. So we used here a hierarchical approach to get ordered networks. And hierarchical approach means we had two end groups. So we had like bromines and iodines, simply because of the fact that the iodines react on the gold surface earlier. So we could synthesize the macrocycles first and then the chains, which are both structurally ordered. And then we could connect them in a second step to create the nicely ordered 2D networks. So after synthesis, these networks on the gold surface looked like this. So we deposited the molecules on the gold surface, annealed the networks to 270 degrees. And then we had the covalent bond formation. And so these look like nicely ordered hexagonal honeycomb networks, although the size of the flakes is not especially large. So that's because the synthesis is kinetically controlled. So these materials, at least from DFT, show that they're having a 2D properties. So if one is looking at the DFT, one sees these are flat layers with an absorption height of about 3.3 angstroms above the surface. One can nicely see by looking at the electronic properties that the valence band is actually homogeneously distributed along the networks, and the conduction band is located near to the newly formed CC bond. So here the conduction band is a little bit outside, and the conduction band +2 is actually sitting directly on this newly formed CC bond. So I introduced before different lattices. So if you're looking at these networks, so we have here two different lattices. So if you're looking at the nitrogen heteroatom in the center, then we actually have a honeycomb network. And if you're looking at the connection of the newly formed CC bond, then this is actually a Kagome lattice. So both of these lattices have at the K point a Dirac cone, and that's what we can also see. We have here like linear dispersions and crossing at the K point. So this is the band structure actually for this network in gas phase. If you put that network on the gold surface and measure spectroscopy, then we already see what I mentioned before. So the bands start to shift, and in our case, this is actually significant. So if you're looking here at the onset of the valence band, then we are below -1 volt, while here it's close to the Fermi level. So we have a downshift of the band structure just by absorbing these networks on the gold surface by about 1.6 electron volt due to charge transfer from the substrate. So in order to get exactly these band structures, we would need to be able to decouple it. We tried it by intercalating some salts, but this worked not out. So another thing which we tried is to synthesize these networks directly on a bulk insulating substrate. For this, we actually used a KBr substrate. Then we have the problem that if we are going from the metal substrate to the insulator, that the overall surface interaction is weak. That is nice for the electronic properties, but it's bad for the synthesis, because if you reduce the interaction to the substrate, then the molecules like to interact with each other way more. So they try to optimize the intermolecular interaction. And for planar molecules, as these triphenylamines, which we used here, this is basically the pi-pi stacking. If you're looking at DFT calculations, we see that the pi-pi stacking of such molecule is energetically way more favored than a planar absorption, for example, through halogen bonding. And that's exactly what happens on the KBr surface. So we start to see here chains of molecules. And if we zoom in, we see like here single molecules which were perpendicularly standing in pi-pi stacks. So that's also not the way how to create these decoupled 2D layers. We have to find here other ways. So most likely like more reactive or thin film materials on a metal will help out there. So it also does not matter actually what kind of insulator you're using. We're trying several ones. So we are using not only alkali halides, we were also using oxides, for example, magnesium oxide, because there we have a different oxidation state. So we hoped that that could help to make the molecule more planar. but you can see on both insulating substrate, these type of molecules try to stay upright and form these chains, and you can always see like the stacks where the molecules are in a normal pi-pi stacking difference to each other. The only difference what you can observe on these surfaces is the alignment is different. So these molecular wires are arranged along 1,1-O directions, and here the molecular wires are on 1,0 direction on magnesium oxide. And that comes simply from the fact that we have different lattice constants, and then the molecule tries to align slightly different. So like here, the molecule is arranging according to this iodine here, and here the molecule is more arranging according to this interaction between the oxygen and the hydrogen. So that's the only difference. So the bulk insulator does not help us in this case to create these nicely planar 2D networks. As I say, we have to find different materials where we can synthesize these decoupled 2D layers. So another way which we looked at to tune the electronic properties of such networks is to check out the functionality of the pores. So these pores have fascinating properties in one way that they can trap the surface state. So we have a confined surface state in these pores. And we have also like the functionalities or functional groups here pointing towards these pores, which are nanometer sized. So that would be also ideal actually to trap some molecules in there. So that's what we looked at first. We used not in the first attempt, not a 2D network, but we used principally just one pore. So we used a molecule which has one bromine missing. And the reason for that is because here we always get 6-membered rings. In the 2D network, this is not always guaranteed because you have strain during the growth and you have a flexibility of the bond. You create quite often 5-membered and 7-membered rings. And therefore we choose here like these rings because they are always like 6-membered. So we looked first for the interaction of a very weak molecule or atom. Actually, we looked at what is the iodine doing in the pocket, and we figured out that the iodine is actually very selectively always going to the same position. So if there is only one iodine inside, then it's always going in front of the CC bond. If there are 2 iodines in it, then you have 2 possibilities. So that basically through iodine-iodine interaction, another one is attaching, or you have simply 2 here in this perspective where they're in front of this CC bond. So here you have an optimization of iodine-iodine bonds. Here you have the preference to sit in this preferred adsorption site. And here you have again an optimization of the iodine-iodine bond simply because the third one is here attaching through iodine-iodine bond. So by looking at the interaction, we see that actually the interaction between the iodine and the network is not particularly strong. So it's usually van der Waals interactions. And the stabilization effects from DFT is roughly like 0.13 electron volt. So it's actually quite a weak interaction. Well, we can also see from charge density different plots where we see that the iodine is mainly interacting with the substrate, but only very little towards this network. But although the interaction is very weak, we see that it selectively adsorbs always at the same position. So then we thought we can use more interesting molecules to trap in this pore and see how we can tune with them the electronic properties. And the next molecule we tried is the trimesic acid, because this has like 3 carboxylic acids, which could nicely bind to these oxygens protruding into the pores. And that actually works nicely. So you can put these triangular shaped trimesic acid into the pores, and you see 2 adsorption configurations. So either these triangles are oriented downwards or upwards. And from DFT, this looks like is the most optimal adsorption position of this trimesic acid in the pore. So forming like here hydrogen bonds to these oxygens. So what is the idea behind? So we were thinking if we have like a 2D network and we can absorb molecules non-covalently, so meaning through just self-assembly, then we would have a nice way to actually tune the electronic properties by absorbing the molecules, changing the band structure, and then we could try to desorb the molecules again and changing back the band structure. And at least from a DFT point of view, this seems to be a feasible way to do. So we looked at the different band structures just for the pure network in gas phase. And here, here is the trimesic acid inside. And we can actually see that the band gap of the network can be changed. So from starting of 1.75 electron volt, we can narrow it by absorbing the trimesic acid in it to about 1.57 electron volt. So that seems to be actually a nice way to go. Experimentally, we will try to prove it now in the next step. So this is just an outlook which shows that this could be like an interesting way to tune the electronic properties of these 2D networks. So in the next step, I would like to switch to another type of networks. So this is like the graphene-based networks. So the graphenes, they are composed of single and triple bonds. These are very interesting materials because they should be also direct comb materials, and some of these networks should also have like an intrinsic band gap. And they are all open porous materials, so they are interesting to, for example, to trap other molecules or atoms in it. The only problem is they're very hard to synthesize. So far it was not possible to synthesize a single monolayer with high structural quality of these networks. So there was a proposal from solid state chemistry that basically you can try to synthesize graphene-based networks. So in this case, like networks which look like a gamma graphene, but in a supramolecular way, because that would give you a structure of the triple bonds, which would look like the gamma graphene. But because you're using, instead of the covalent CC bond, like a supramolecular bonding motif through hydrogen bonding, you should be able to achieve like a good lateral order. So we try to do that also on the surface. We synthesize the molecule, put it on a gold surface and on a silver substrate, and we can actually see that these supramolecular graphene networks through hydrogen bond form quite nicely. This is also related to the fact that this bonding motif with the hydrogen bonding here to the nitrogen is actually energetically the most favored compared to other more open porous networks. If one is looking at DFT, one can actually see that these networks are more or less planar. So there is just a slight buckling through the acetylenic unit here, but otherwise they were relatively planar. So in the next step, we were thinking like these molecules are usually more reactive if you replace the hydrogen by a bromine, and the bromine usually has this sigma hole. So meaning it has a positive charge at the end, and that would actually also fairly nicely fit to this negatively charged nitrogen. If it is also possible to form such networks through bromine, nitrogen, halogen bonds. So that would be the suggested structure. We tried that on the surface, and indeed that works. The only thing you have to do differently is you have to prepare the surfaces at low temperatures, because otherwise the bromines will already cleave off on the gold substrate. So by looking at high resolution images at different bias voltages and compare that to calculated STM images, we could actually identify the bonding motif, and indeed we have like a bonding between the bromine and the nitrogen of the triazine unit. This is actually surprising in one sense, because usually one knows the self-assemblies of the bromines, that they form this X3 symbol, so that the bromines have this free or triangular shaped bonding motif. Another one which would be possible would be like rather such a 6-fold bonding motif. But looking at the interaction energies in gas phase, it actually clearly shows that the halogen bond between the nitrogen and the bromine is the most stable one. And that's also the reason why we observe it on the substrate. And actually what is even more fascinating is normally one thinks that the hydrogen bond are quite a stable molecular interaction. But if you compare it in binding strength to this bromine nitrogen halogen bond, this is actually even more strong. And the reason for that is that this halogen bonding motif is more strong, is that the halogen can also interact with the triple bond here, and therefore the overall interaction energy is larger. So this is just a supramolecular network, so it's not yet a molecular network, which we could call like a 2D material where we have like an electronic transport along. So for that, we do the next step. We basically try to anneal these molecules on the surface. So this is the molecules once without the nitrogen in the core, once with the nitrogen in the core on a silver surface. And we can see that they form nicely honeycomb networks where we have the molecules at the corners and the blobs in between are actually metal add atoms, as you can see it here in the cartoon, which connect the two molecules because the bromines are already cleaved off. So this is like a honeycomb network. And again, what we expect is like that we have some Dirac-like behavior on the K point. And it would be otherwise also very interesting material because we can see that we have here actually at the Fermi level some bands. So these are the calculations in vacuum. If we put that molecular network, in this case, it's the one with the bromine and the nitrogen here, then actually we find that the bands are shifted downwards by roughly like 2 electron volts. So these bands, which we can see here, are actually then shifted down. And what happens is that we have basically like a semiconducting material. So here also, what we would like to try in the next step is actually to decouple these organometallic networks from the metallic substrate, that we have like these nice electronic properties preserved. Nevertheless, what we could show by looking actually at the different electronic states. So here in this spectroscopy measurements, you can actually see the unfilled states. So that's in this case, it's then conduction band +1 and conduction band +2. And if one is recording it from the molecule over the metal atom to the next molecule, then one can actually see that certain states, for example, this conduction band +1 is like nicely distributed over the entire network and also over the metal add atom, which is basically also predicted by DFT calculations. So we have here like nicely extended electronic states, although these are just metal organic networks and not completely CC bonded networks. So actually we try to look into the next step and to go from these metal organic networks to the carbon-carbon based networks. And on the gold surface, we used here the molecule without the nitrogen. This works actually if one just anneals these organometallic networks to higher temperatures, roughly at 590 K. But these molecules are very fragile. So if you heat them too much, the molecules start to decompose, as you can see here. And it's actually fairly difficult to get rings or a certain amount of rings which are just covalently bond like that. So that was one of the more successful tries we had. So we can compare that to the silver surface, which I presented you so far. So there we have the same networks at room temperature. And we also try to see these organometallic networks if they're stable at room temperature. And that actually works. But if one heats it, then one can actually see that on the silver, we do not see the CC bond formation at 470 Kelvin, but we see that the networks are actually becoming more nicely ordered. So they try to crystallize. That one can also see that we start to see characteristic defects, which we are also known from graphene. for example, these 5 7-membered defects or these 8 5 5 defect lines. So we try to understand why is the difference on gold and on silver. And one indication we found is if we looked at the borders of the islands, they look different on the gold and on the silver substrate. So on the gold, there seems to be always a termination by a metal atom, which are highlighted here by these arrows. So this seems to be like the terminating bonding motif. So this seems to be the stabilization through the metal atom seems to be favored. On the silver, it's different. If one looks at the edges of these networks, you never see here a metal atom which compensates the unsaturated bond. But we think the unsaturated bond is actually more binding towards the substrate. And if one thinks in terms of making a CC bond, that would be like an unsuitable bond geometry. So therefore, we think it's more difficult to create the CC bond on the silver surface, and that's what exactly we see also in the experiment. On the other hand, well, we also have to take in account to form the CC bond, you need to break up the metal organic bond. And that seems to be actually easier on the gold surface. And that also explains why on the gold surface, usually the CC bond formation, it takes place at a lower temperature. So overall speaking, what we see that on the silver surface, because it's hard to form this covalent CC bond, we have a larger temperature window to actually crystallize these 2D networks. So as a last point, just to give you a quick outlook, what we are currently working on is another way how we can use on-surface synthesis to actually change in a very controlled way two-dimensional materials. So the thing what we want to do is to use on-surface synthesis to actually change graphene. So there is a nice example from the group of Johannes Barth and Willi Auwerter, where they used, for example, tetrapyrrole rings, and they fused them covalently to graphene flakes. So our idea was, what we wanted to do is actually to see if we can incorporate porphyrins into a graphene flake. And the approach which we chose was to use kind of fancy designer-made porphyrin molecules, which has a lot of carbon rings around. And the idea would be that you're using a very reactive substrate, for example, platinum, and then you deposit the molecules there. So that looks, because you have so many phenyl rings and you have sterical repulsion, quite complicated, and there are also different adsorption possibilities. And then you heat the molecule on the surface, and the idea would be that you make a dehydrogenation, and you would start to form like a cone-shaped feature. And if you try to anneal further, that basically carbon from an unclean platinum surface or unclean platinum crystal can attach towards these porphyrin molecules, and that would be a way to incorporate porphyrins in graphene flakes by on-surface synthesis. So these are the first preliminary results I can show you here. So here is this porphyrin molecule on the platinum 111 substrate. So at room temperature, one sees the molecules, but we have different configurations simply because there are different possibilities due to steric repulsion of these side groups. And if we anneal these molecules to about 740 K, then we see the dehydrogenation taking place, and the molecules start to form like these cone-like features. And if one is looking carefully, just around 740 K or a little bit higher, depending on the preparation, one can actually see that some of these cones are getting larger in one direction. So usually only in one direction, because if one thinks about one would attach carbon in a homogeneous way, then you would create like a cone which is lifted from the substrate that would be energetically not stable. So you would attach the carbon on one side. And that's actually what happens here, in this case and in this case. And if you simply heat even further to about 920 Kelvin, then actually what we find quite often on the surface is that we have graphene flakes starting to grow. And in these graphene flakes, we always observe these cones. Sometimes there are also cones beside. They have similar structures. And therefore, we think actually we can incorporate by on-surface synthesis here these kind of porphyrin cones. So that would be a very nice possibility to actually then incorporate metal atoms into the graphene lattice with very well-defined coordination bonding motifs through the nitrogens. So this is just an outlook to show you what we can also do with on-surface synthesis. So in the first part, I showed you like these 2D networks, which we can nicely create on the surface, and we can use their host-guest interaction to trap molecules and also change the electronic properties. Then I showed you how to synthesize these graphene-like networks. And as the last part, I gave you an outlook how we can change, for example, for very nice incorporated defect sites of porphyrins, graphene flakes by on-surface synthesis. And with that, I would like to thank for your attention, and I would like to thank my team for doing all this great work, and the collaborators for synthesizing the molecules, and also the collaborators from Fiori to actually provide us with DFT calculations. Thank you very much for your attention.
Thank you very much, Sabine, for very exciting talk. And now I'd like to ask the people in the audience if they want to ask questions. Let's try. So everyone will be now able to open their mic, in principle. So Jorge, you wanna try? You wanna be first? If you know how to open your mic.
I know how to open, but I don't know if I should. I mean.
Okay. Please go ahead, Jorge.
Okay, Sabine, thanks a lot for the nice talk. It was really inspiring. I basically have 3 questions, right? Okay. The first one is when you were discussing about these COFs that you were doing with that you could you know, deposit these gas molecules inside of the pores. My first question is, of course, I guess that the atoms would do the same function of changing, of doping. Have you considered which atoms would be interesting to use in this case, or calculated which ones you could also have to also change the position of the Fermi with respect to the bands?
So you mean this COF, and respectively what kind of atom to introduce here? Is that right? Or?
Yeah, exactly.
So basically, we just looked at these 2 examples. So we looked the iodine because that we had from the on-surface synthesis anyhow. And then we looked at the trimesic acid because here we actually were interested to see if we could also do a reaction like a covalent one. So if we could actually form here a covalent bond. Okay. But that did not work out because actually the trimesic acid desorbs before. That's okay. Good and bad because it could be like a supramolecular doping.
Yeah.
But the reaction for that, the pore is too small. You need larger molecules. But otherwise, we haven't made any calculation for other atoms or molecules.
And I guess that you also see the surface state confined within the pores, right? I mean, that would be my
actually,
guess.
I think there is like a minus sign missing here. So.
Okay. And last but not least, have you? I like this very much. These networks that you generate with metal organic, you know, with the silver and the gold atoms. Did you measure ARPEs? I mean, if there is some kind of band structure generated apart from the calculations, because they are really nice. I mean, I find it exciting.
I mean, we haven't looked at that. I mean, it would be very interesting because now we know how to grow them very large rangely ordered because we know how to crystallize them. So we know which surface would be nice to do the experiments, but we haven't looked into it.
Well, thanks. It would be really interesting to see the bands that get formed. Yeah.
I agree.
Thanks.
Okay, so we have another question by Onar.
Hello. Could I ask what was the size of the biggest graphene flakes you managed to produce with this method?
So the graphene flakes, so you mean these kind of things where the porphyrins incorporated?
Yes.
Or it depends. I mean, we did not, I mean, we tried also to dose ethylene to actually grow larger flakes. So this one is just basically from the platinum crystal, the carbon was segregating to the surface. It's depending, I mean, we can make a full monolayer, that works.
But I mean, wide, how wide did you manage to make those flakes?
I mean, it depends on how much carbon we have on the surface.
Okay.
So in this case, we just segregated the carbon to the surface. That's why the flakes are small.
Okay.
But it was nice for us to see, but we can also intentionally dose more carbon on the surface, and then the graphene layers are becoming monolayer-like.
Okay, thank you very much.
Okay, thank you. Next question comes from Bruno Schuler. Please go ahead.
Hi, Sabine. Very beautiful results. So the main challenge really seems to be to bring these networks to a decoupling layer, right? So you tried strategies to grow them directly on like salt films and so on. How do you see the chances to transfer them post-synthetically, especially the ones which are covalently linked, the stable one, for instance, viscoelastic stamp, or to dissolve the gold and then kind of fish it from the solution? That's things what other people try for 2D materials, but I have no clue or like no intuition how it will work for molecular networks.
I think it will be possible. I mean, the only problem one has is that the networks are relatively small. So the fishing is probably challenging because it's really fishing. So you have to look for them. And I think the other thing which might be a problem, but that one we'll need to look into, is that we have like more functional groups. So it's not only just carbon, but there are some other atoms in it, like oxygen and the nitrogen, if they would react. But I think the chances would definitely be it's a gold substrate to dissolve it from the surface and then to try to transfer it.
Okay, thank you.
Okay, if there's any other question. If not, we are right in time.
I have a question.
Okay, go ahead.
May I go on? Yeah, very well. I'm Isaac. Just so I mean, for instance, in the experiments of one of the co-organizers of the session, Cesar Moreno and Aitor Mugarza, they managed to do like a 20 by 20 nanoporous graphene also from a bottom-up approach. Whereas here, really, it seems that with these hexagonal molecular frameworks, it's more difficult to get to those sizes. So what do you think that it's, because I mean, it's the same kind of type of reaction, more or less. It's the Ullmann reaction, right? So what do you think is the limiting factor to get?
I mean, you can get larger networks. That's not such a problem in sense of like you can just add more molecules. But the question is if the quality is still good, because with the hexagonal network, it's more easy to like incorporate 5-membered and 7-membered rings. So
Okay.
the square symmetry is more stable because the stress you will create if you create the 3-membered ring and the 5-membered ring is then higher compared to the 4 than the hexagon where you can go to the 5 and the 7. So we can make more dense networks. That's not a problem at all, but the quality is then not better because you still have defects of 5-membered and 7-membered rings or boundaries where you have unconnected flakes. So we choose a lower coverage, but then the flakes are basically just the hexagonal network.
Okay, I see. Thank you. Thank you very much.
Thank you, Isaac. Okay, so I guess now we should be moving to the next talk. So thank you very much, Sabine, for your inspiring talk.
Thanks.
And now we'll welcome Jorge Lobocheca.
Okay,
Sure,
getting ready. Do you see my screen?
Yeah, perfect. So Jorge is going to talk about also extended organic nanoporous networks. Jorge is coming from the ICMA at the University of Zaragoza. And well, go ahead, Jorge. Thanks for joining us.
Thank you very much, Aran. I'm missing the part of the conference where we go for beers and we enjoy a little bit of the pinchos of Madrid, but okay, I mean, these are special circumstances. So I guess everybody, we have to all live with it. Anyhow, it's my pleasure to be here and to talk to you today. And in fact, what I wanted to share with you is the fact that it's the work mainly from Iñaki Piquero Zulaika, which was my former PhD, and now it's working in Munich in the group of Johannes Barth. And I'm going to talk to something which is not exactly like Sabine has discussed. Sabine was discussing about the orbitals or the electronic orbitals that were made from the networks. What I'm going to discuss now is what the networks do to the surface state, okay? So to the electrons coming from the substrate. And in this respect, we're going to, let's say, go a step ahead of the quantum corals that were predicted in the 90s and demonstrated in the 90s, as you will see in my introduction. So the introduction will be very simple. First, we will start with discussing about the surface electron confinement, and then I will show you how band structure is made up by these molecular organic networks, by the barriers generated by these molecular organic networks. And then I will show you that we can engineer, we can tune these surface states by changing the morphology of the networks, like for instance, changing the barrier width, introducing metal coordination atoms, and even depending on the position of these metal coordination atoms, you can have different possibilities of intercoupling through the conductive, let's say, for making channels. So let's start. First of all, I started with something very simple, which is surface states in noble metals. We know they have electrons on the surface, and these electrons are free to move over the surface, so that when you have an atom or you have some kind of thing on the surface, you generate a ripple, and this ripple is nothing else than the scattering of the surface state electrons. So that then when you make circles or you make any closed structure, like in the group of the Nigler, you can find that the electrons are trapped within these zero-dimensional structures, okay? So this was very nice because when you go with a tip at the center of one of these structures, you can obtain this kind of spectra, which is formed by several peaks with different width. And actually, you can find that these structures, the width is not a delta function. So that means that the electrons can still tunnel out of these structures, okay? Now, if you go for increase the dimensionality, let's say, and you just make like a straight step, everybody knows that you can combine electrons within these 2D networks, within these two lines, within these two steps, and you can find these quantum Wells states, okay? Now, the nice thing comes when you have a repetition of these steps in a very regular way, like for instance, in vicinal surfaces. In that case, you get bands, and these bands are just a picture of what you have, what is the size of these terraces, and what is the material that you have. So what is the starting surface state that you have? So we wanted to go to molecules, and the reason for going to molecules is because first they scatter the electrons just like the atoms, but then you can have self-assembly, and this self-assembly guarantees that you can generate these structures in a long range, okay? And this is very nice, very convenient, because of course you can play around with things like the potential barriers, the width, and then the distance between the barriers, just by the position of the molecules and letting them react and generate this kind of network. So it's really, really convenient. So what we wanted to do was to actually go and ask ourselves what happens with the zero-dimensional confinement. What happens when you replicate these quantum corals that I was speaking at the beginning? And this is something that was just hinted by the group of Professor Barth in Munich. Basically, they generated this network using this molecule, these 6 phenyl rings together with 2 cyano groups at the end, and mixing cobalt and without cobalt. This is just molecule, sorry. And then they basically saw that the electrons were confined within the hexagonal pores and the triangular pores, as you can see over here. So when you go to the crosses, black crosses, here you get one of these spectra like we were expecting, like in the quantum corals. But for us, we said, okay, let's try to do something which is replicated, periodic, and which extends throughout the surface. And we got this through making this network with these Perelin derivatives over here. So we got this network, and then basically we obtained that the electrons could be trapped within these pores, each of these pores. So if this is your initial spectrum of the metal surface with the onset of the surface state here around 0.4, then when you measure at the center of one, at the center of one of these pores, you basically get a peak at 220 millielectron volts. But actually, you can use ARPES now, angle resolved photoemission, in order to find what is the real band structure of this. And this is what we did. Here you can see this is the photoemission spectra as a function of the initial state energy and the parallel momentum. We see that in the copper, it's looked like a parabolic shape. And this is because the electrons are free to move over the surface. And one thing I want to point out is that the onset of this surface state in STS, which is this point over here, coincides with the fundamental energy of the band, so the bottom of the band. Now, when we have the network on the surface and it covers the surface completely, basically the band structure transforms into this shallow dispersive band. And if you look into this shallow dispersive band coincides in energy with this peak here that we know that locally it's trapped within the centers of the pore. So this was the first evidence of a quantum dot band array. And now the thing is that we can try to see if we can engineer this band. This band that I repeat, it comes from the confining of the electrons within trapping it within the pores. So the network is the barrier, right? It's not an electronic state generated on the network, right? It has to do just with the barriers. And one of the things you can do to tune it is, of course, change the pore size. Like, for instance, just using the same types of molecule, just with 6 or 4 rings, right? You can trap the electrons within the pores. And this is the two images are of the same size. You can basically see that when you go with a tip probing at the center of the pore, you can see that there are differences in the two types of spectrum, right? So there are shifts related to the size of the pore, and this shifting depends on the size of this pore. Another thing you can do is to change the potential barrier, and this is very simply done by changing the registry with the substrate. And by changing this registry, you basically interact differently with the surface, so the barriers of the network changes, and that modifies slightly the surface state. But one of the things that was still missing was the possibility to tune the barrier width. Okay, and this is what we did in this work that we published a few years ago. Basically, this is the molecules that we used. We used this molecule with a thiophene group. So here you see a sulfur that made this network that you can see over here. So this is a hexagonal array, just made my molecules. So the bromines are just making the bonding, this halogen bonded. And what you see is that the pores are separated by one single molecule, okay? And this is extended throughout all this network. On the other hand, you have this situation over here with that when you change to a furan group here, so when you put an oxygen here, just see that the two molecules are identical. You just change this oxygen atom here. Now this oxygen is more electronegative, so it interacts with other molecules, and then you generate a double wall. So you have two molecules between the two pores. The networks are still extended throughout the surface, and you see that the two are exactly the same except in the size of the pore instead of but you just have two barriers in between the two, or one barrier. Now we looked into the locally with STM, and we checked what was if the electrons would be confined within these pores, and actually it did. Here are the spectrum on this side. This is the initial silver 101 surface DIDB, the conductance map, the conductance spectrum. And then this is the one for the single wall. So that means this guy over here. And the green one is the one for the double wall. So the one that has two molecules between the pores. Now, when you go into these energies, basically you see that the electrons are contained within the pores as expected. So that's very nice. However, if you now look at this, you can immediately see that there is something weird. Here, in principle, the barriers are thinner. So you expect the surface or let's say the confined state to be closer to your onset, right? Whereas if you put a double barrier, you expect that the confinement is better, so the energy goes high. But here what we have is the peak swap. So we could not understand at that time what was the reason for this. So we decided to do angular self photoemission on this and find the band structure. To our, we felt very good when we got these data sets, because basically if we start with this surface state, okay, this is the one from the surface, and then we deposit the first network, this one over here, then we find that this is the band structure that develops. As you can see, we have the onset of the surface state is lifting up, it's going towards the Fermi level, and you see that this is the typical shift expected for a confinement. But if we generate, on the other hand, this other network on the surface, we can see that the onset is even higher. So you can see that the energy is raised with respect to the single wall case. And that made us really, breathe easily, because we could actually find that the confinement was better when you have a double wall. So the question is, what is actually looking at? The STS, what is actually looking at, right? And we found out that when we compare now the STS with respect to this band structure, what we find is that the STS, what actually is probing with more sensitivity, is the top of the band, as you can see here. So the red point or the red peak is really marking the position of the endpoints, and the green one is marking the position of this other one. So the onset of the peak that you would have is the one that is giving you the fundamental energy, not the peak energy. And this is something to do with the way that the wave function extends into the vacuum. Anyhow, to make it simple, the most interesting thing here is also that the dispersion of this band is shallower than the one that you have here. And that's related to the fact that the electrons are kept within the pores here it's more easily kept, so they cannot interact with the next neighbors as easy as the ones when you have just a single value. So, of course, the next question was, can we tune also now these band structures when we introduce metal organic atoms into the picture? And this is so nicely because you can have a very nice and rich myriads of networks on the surface. And actually you can get quasi-crystalline structures, you can get magnetic properties because these atoms can be made of cobalt or nickel, or you can even have topological properties of these networks. So they are really interesting. But we wanted to see what was the effect of these metal organic networks for the confinement of the surface states. And we use the networks, we use the recipe that obtained by the group of Johannes Bath using these polyphenylene molecules with cyano groups and adding cobalt atoms. But instead of doing it on silver, we did it on gold. And of course, when you do it on gold, you also see that the electrons are confined within the pores. So now we looked at the band structure and hope to just change the pore size, so see changes on the position of the band structures. And actually, this is what we observed with the angular self-photoemission. Here is the onset. So here is your initial two-dimensional electron gas, the one with both surface state, with the splitting due to spin orbit coupling. But when we deposited the larger molecule and we made this network, we obtained this kind of band structure. And when we did the smaller molecule, we obtained this one. Now, if you look at it, you say something is weird, because instead of the energy of the two-dimensional electron gas, meaning this one, the fundamental energy, instead of going towards the Fermi level, so rising because of the confinement, we saw that the energy went down. And that was extremely weird. So we started to say, okay, let's try to simulate what's going on and check if we can at least model these bands. And we could do that, but instead of having the normal reference of the surface state, which is at 450 millielectron volts, we needed to renormalize this surface state and lower this energy. So it seems that something is doing an effect of shifting down the initial surface state, okay? And this is a scaling with the number of molecules or atoms that you have on the surface. So for us, that was really weird. So we thought, okay, let's do some DFT calculations. In this way, we contacted Professor Arnau, Andres Arnau from San Sebastian. And he did these calculations for us. We ignore the molecules because the molecules in principle are, we know that they are only confining the electrons. They are not changing strongly the position of the surface state because we had some examples previously. So the idea would be to make a grid of isolated atoms on the substrate of gold. Like for instance, this is a 2 by 2, this is a 3 by 3. Now, in principle, you cannot do this kind of experimentally. You cannot obtain this because if you deposit the atoms, they tend to aggregate. So you would not be able to get this experimentally, right? You need the molecules to actually separate them and locate them very well one from each other. So when he did when he calculated, Professor Arnau and the group calculated this kind of band structure, they actually found that if this was your original surface state, they actually found that the presence of the cobalt atom shifts down these changes the position of the surface state. So there is a renormalization of this surface state. And this is the fact, this is what is changing it down, right? And this depends on the density of atoms that you have on the surface. He also did the calculations for copper on copper 111, gold on gold 111. So we thought, okay, is this something real? Is this something which can be extended to other networks? And the answer is yes, because we deposited a totally completely different molecule, like the one that you see over here with 3 pyridine N groups over here with a phenyl ring over here. And basically, when you deposit it on copper 111, the molecules just generate this network that you see over here, very nice, very regular. And when you look at the band structure, you start with this one before you deposit the network. When you form the network, you get this one, and you also see that you have a downshift of the surface. So actually, this seems to be general, because if you add an extra ring now on these molecules, so now this is the same initial molecule, but now you're adding in each arm a phenyl. You also see that there is this downshift. Now look that it's independent of the shape of your network. This is hexagonal, but this one is just a demi-regular network. And you can see that there is no hexagonal order, but you get still this downshift of the surface state. So indeed, the metal organic, so the metal coordination, the atom, what it's doing is redefining the energy of this surface state. And on top of that, you have the electron confinement from the nanocavities, okay? So this was a very interesting, let's say, result that we had. But in the last minute, I have to speed up. Basically, we also studied a little bit more in depth what was the role of this metal coordination atom if you put it on the side. And basically, what we found out was that when you have the metal coordination on the side, the electrons can really tunnel easily to the next pore. So basically, what you have is that the electrons can go from one to the other, whereas the molecules really reflect these atoms easily. So you can not only the fact that you have metal atoms is important, but also the geometry of where these metal atoms are. So just to conclude, I hope I was showing you that we can really tune easily the electronic structure of the confinement of the surface state, and we can really play around with the band structure that we have. So these are the people I have to acknowledge and the funding, and this is the group I'm working now in Zaragoza, and this is a user facility. So if you are interested in using STMs, please come and visit us, because we will give you access to one of these equipment. So thank you very much for your attention.
Thank you very much, Jorge.
I'm sorry for
really nice. Too bad you had to speed up at the end.
Yeah, well.
So if there is any question from the audience, now it's time to. Okay, so Juan Moreno Lopez, if you can ask yourself.
Yeah. Hi, Jorge. Thank you very much for the talk. I'm wondering, the downshift that you see in the surface state is related only to the cobalt atom deposition, or it had also some influence the order of the cobalt atom? I mean, if you deposit only disordered atoms of cobalt, would you expect the same shift?
No, if you, I mean, the position of the adatoms is important. You have to have the lattice, otherwise you won't get the band structure formation in an easy way, right? I mean, there has been studies of people depositing adatoms on a cold substrate, and you don't see. I mean, locally you see that it's going down, but it's more, let's say, complicated when you don't have an order. Here, I believe that the idea is to actually have them separated. And for that, if you want to make this, let's say, effect relevant, you have to have something that orders it so it disperses regularly on the surface. Okay?
Okay, thank you very much.
Thank you, Juan Carlos.
Any other question? No?
It was too long.
Okay, so maybe because we are running a little bit late, then maybe we can move on to the next talk. Thank you very much, Jorge.
Thank you.
And so the next speaker is Bruno Schuller, who I believe is now in EMPA, but has recently moved from Berkeley. So probably the work he will be presenting comes from Berkeley, I guess. And he will be talking about designing atomic quantum defects in two-dimensional semiconductors. So please, Bruno.
Thank you, Aaron. Thanks a lot for the introduction. Yeah, that's correct. So I recently relocated, but all the results that I will show you today will still be from the Berkeley National Labs. So today I want to basically share a cross-section of some of our work where we looked into point defects in two-dimensional materials, in particular semiconducting transition metal dichalcogenides. These class of 2D materials is very interesting, and many of their peculiar properties come from their interesting band structure, which are heavily influenced by the d electrons of the transition metal, particularly around the band maxima, and also, of course, of the strong out-of-plane confinement in these 2D materials. But to talk today, I want to rather focus on how we can engineer the band gap of these 2D materials by point defects, or for instance, like substitutional defects, or really putting impurities in these rather uniform 2D materials, and how we can harness their quantum properties, as for instance, their electron spin for fundamental research, of course, but also then later on to use them in quantum technologies. We study these 2D materials with a bunch of different scanning probe methods. I don't think I need to explain a lot how this works, of course, but in essential, it's non-contact AFM with CO tips to look at the atomic structure, STM and STS to look at the electronic states, but then also STM luminescence, so injecting electrons at higher energies, and look at the emitted photons to study optical transition at these point defects. So that's how a sample looks like in our case. In this case, for tungsten disulfide, grown on epitaxial graphene on silicon carbide by chemical vapor deposition. And this turns out to be a very nice substrate because you have a very weak van der Waals bond. So this really preserves the interesting properties of the TMD on these surfaces. So they're actually grown outside of vacuum, and they are stable. So we just can bring them through air in our vacuum low temperature STM chamber. And they already come with a bunch of different point defects, which we try to study in detail. Of course, this varies a lot on how you grow these materials, but for CVD grown samples, they turn out to be rather reproducible. So most of the time we see actually that at sulfur sites, there is oxygen incorporated. This is the most abundant defect, but there is also transition metal substitutions, for instance, like chromium or molybdenum that substitute for tungsten. And they just happen to be in your precursor material, and it's a low energy defect to form, so they just naturally end up also in your sample itself. But today we want to rather focus on defect that we can create on purpose. And there is a variety of ways how to do that. So for instance, by annealing the sample in vacuum, you can form vacancy defects. or by chemical doping. So by putting intentionally some different precursor during the growth, you can introduce different things, but also by tip manipulation, atomic manipulation, which will be discussed in a bit more detail. And then also, for instance, other ways by helium ion beam bombardment, for instance, you can do that as well. As a second topic, we will look in detail into a specific defect which has some interesting properties, and if there is time to look at STM-induced luminescence at a point defects. So first, I would like to start with a little bit of controversial discussion in the field, and this is the influence of vacancies. So this is commonly assumed to be the most abundant defects in TMDs, and many properties are associated with those, indirectly at least. But in our samples, we really find there is no vacancies whatsoever, which I think is not too surprising, because if you have a vacancy, so we can create vacancies if you annihilate the sample to very high temperature, to like 600 degrees in vacuum, we see these two nice in-gap states, and they make this defect very reactive. So they're highly unhappy. So they try to bind any other thing essentially that is floating around. So you need to keep them in vacuum to stabilize it. So again, we find most frequently this oxygen substituting for sulfur, which has a very different electronic structure. There is one defect which we also happen to be able to create, and this is the carbon-hydrogen complex. So by a post-synthetic plasma treatment in methane, we can introduce carbon-hydrogen impurities at sulfur site. And they're interesting because, first of all, they are charged. So that's why they look so dark in this STM image here. So as compared to other defects, which are rather tiny. So this is a really an electrostatic effect. So because they're negatively charged, they bend the bands upwards. So that means in the unoccupied states, the conduction band is depleted. So that's why you have this basically this black hole forming at negative bias. It turns out to be bright in STM images. So that's really an electrostatic origin. And there's something interesting we can do with these defects, and this is to remove the hydrogen. So at rather high voltage and current, we can shoot off the hydrogen from this carbon-hydrogen complex, and in a rather controllable fashion. So we can go one by one and remove all this hydrogen, and then you see something rather drastic is happening. So in AFM, just this little blob is going away. So this is just removing the hydrogen. But in STM, you see this bright orbital feature popping up. You can also do that in a bigger scale. So you just scan around, and this is a rather efficient and reproducible process. But what is really happening electronically is shown on this slide here. So first you start out with the CH complex again, so which is negatively charged. So you see this nice band bending at the defect sites, and actually at the occupied states, we see the formation of different bound and resonant hole states. So that's an attractive potential for holes. So we see a variety of S and P-like states forming in this attractive potential. That's very interesting physics too. Unfortunately, I don't really have time to go into this in more detail today.
Bruno, sorry to interrupt you.
Yes.
You believe we see your pointer, we don't see it. At least I can.
Sorry. Okay, I'm moving around. Yes. Sorry about that. I was pointing like wild. So, but okay, maybe this would have been more distracting. But thank you for pointing this out. So yes, so down here, so these are the occupied bound hole states. So if you remove the hydrogen, we see something is happening, and this is like the formation of two bands. So one in the unoccupied state and one in the occupied state. And the same or something similar is happening also in other materials. So in tungsten diselenide, for instance, we find the same defect, so the CH group. But when we shoot off the hydrogen there, we only see one state forming, which is completely unoccupied. And when we map out these orbitals associated with these states, so they're shown here, they look fairly similar. So what we believe is happening that in the case of tungsten disulfide, we have a singly occupied electronic orbital. And in the tungsten diselenide, we have a completely unoccupied degenerate orbital. So, so this splitting comes from two things. First of all, there is a Coulomb repulsion. So basically separation of the electron and the hole, because there is some charging energy which you have to pay essentially, but there is also spin polarization which contributes to this splitting. And the reason why they are different is because of the different band alignment between tungsten disulfide and selenide with the underlying graphene substrate. So the graphene actually donates the electron or fills that defect state, if you want, in the case of tungsten disulfide. That's how the calculation look like. So again, we start with CH, we remove the hydrogen. There we on purposely put an extra electron inspired by our experiment because we see it's charged. And there we see that actually the spin polarized state is quite a bit more stable than the non-magnetic state. So by more, I think it's roughly 150 milli-electron volt, which is quite significant. We see the stabilization of this spin 1/2 state, where one state is occupied and the other one is empty. And that's how the magnetic moment looks like. So it's highly localized at this carbon impurity site. And then because we have this magnetic moment, and in TMDs, there is naturally a spin polarization of the valence band happening, we see actually that the degeneracy between the K and K prime valley is lifted by just because you favor one spin polarization over the other because of the local magnetic moment. Now let's talk more about this fine structure, which is, now it's frozen. Let me see. I'm not sure whether it's me completely. Okay, can you still hear me?
Yeah, perfect.
Okay, good. Sorry. So here is some fine structure associated with this orbital. So we see a series of equidistant peaks, essentially, which comes from electron-phonon coupling. So if we inject electrons or inject holes into these orbitals, you excite also vibrations of the lattice. And these modes have certain intrinsic and resonance modes, essentially, which couple most effectively to this transition. And very interestingly, they are different for the unoccupied and the occupied one. So for the unoccupied state, this can be characterized by a very nice Frank-Condon-like behavior with only a single mode dominating the most. So this is on the order of a Young-Rees factor, which is this electron-phonon coupling constant of about 5. So it's a rather strong coupling of this mode. And on bilayer, we see that too. It's actually the same mode, but the coupling is weaker. And this is just the reason for this is because in the bilayer, you have a more delocalization of this defect state into the second layer. So the couplings or the reaction of the lattice is a bit less strong. And there is also difference between the unoccupied and the occupied state. So this is really kind of a signature of spin phonon coupling. And there, not only the frequencies are a bit different, but also there is more modes that contribute, and the strength is also quite a bit different. So just by the shape, you see the coupling is different, despite the fact that the electronic wave function is rather similar. And this is also reproduced by theory. The same things essentially. We have a single mode for the unoccupied state, which is essentially this one here. So a breathing type mode. So the carbon and the sulfur move against each other and the tungsten basically go out of the way. And in the occupied state one, the distribution of couplings is quite a bit different. And especially we see this high energy mode around 75 millieV, which can be attributed to this carbon moving up and down. And this couples more strongly for the occupied state. Then that's the summary. So what we can do with this system is reshooting off the hydrogen. We can have an electron that goes into this dangling bond of the carbon. We see a spin polarization of this state and a very defined vibronic coupling to only a few vibronic modes or local vibronic modes. Then very briefly, the last part of this talk is on STM luminescence. So what we can also do is we can inject electrons at rather high bias. So you see around 3 volts, 2.5 volts. And what we observe there is that the electron essentially can lose energy on its way and also to excite photons. And this excitation of photons is very local because the injection by electron or the excitation mechanism is extremely local as well. And these photon maps, they resemble essentially the defect orbitals, which happen to live at a much lower energy. And this mechanism works in the following way. So if you have an electron sitting here in the tip, so that's the density of states of the tip electrons, and that's the tungsten disulfide. So it can either go elastically into the conduction band of the tungsten disulfide, or it can tunnel inelastically. So by going from a tip state very high up into the defect state, which lives in the band gap of the tungsten disulfide. And this process is more likely if the photon density of states in this gap, or it's like a cavity or something you can imagine, if the photon density state is high. And this is high at the plasmon frequency. So we have a gold tip, so there is a lot of plasmon modes with a rather large distribution of energies. So in this mode, you have kind of a Purcell enhancement, and that's why we see photons coming out especially at these energies. But there is still a continuum, even though it's like a single electron, single photon process, there is a continuum of photon frequencies or photon energies, because simply you have electrons that can tunnel from a continuum of states into this single defect state. And that's the summary of the talk. I hope I could show you that indeed these are interesting quantum systems, and then we can create these defects in these TMDs in various different ways. And this carbon radical ion is a very nice spin 1/2 defect system. And also want to acknowledge my colleagues and of course you guys for your kind attention.
Thank you very much, Bruno, for your very nice talk and for being so much in time.
Thank you.
So now the mic is open for questions. If there is anyone in the audience who wants to pose a question. I have a small question myself.
Sure.
Regarding these carbon radicals, where you see this spin state, you always look at isolated defects or carbon radicals. Do you happen to have some like neighboring radicals or something? Do you see any kind of interaction between the spin states or anything like this?
Well, that's an interesting question. Of course, we always look also into dimers and so on. This one, I don't think we ever measured them so close together. So the thing is, the defect density is can be high, so in the percentage range, but on average, the defects are still quite far apart. So because the defect states are so localized, you basically need a nearest neighbor or a next nearest neighbor on a sulfur site to see this hybridization. We studied this hybridization for chromium quite a bit, but there was essentially just a combination of atomic orbitals, if you want. Here it will be more interesting because of the spin interaction. And of course, we want to see some signatures of the spin. So unfortunately, this was not possible here. So it didn't show any signs of Kondo or so on, because just it's on graphene substrate. You wouldn't expect to see Kondo there. But of course, like other spin system, or like if you have a magnetic field, you could see a spin excitation. So this is next on the bucket list, of course, to see that.
Because if you have two of these CH close to each other, then you can, and if you can induce disruption on one or the other or both, that's
exactly
nice.
It's a nice toy model.
I have a question. Sorry.
Sorry. There is someone.
Yeah.
Manuela Garza goes next.
Okay. I was just to ask about the Kondo possibility, and he just replied. So I think.
Okay. Okay. Thank you, Manuela. Okay, so now Mr. Ramahan, if you want to...
Yeah, I have a question, so maybe I missed it. What was these measurements were done in room temperature or at low temperature?
It's all low temperatures, all 4 Kelvin measurements.
Okay, yeah, because I was missed it. And another one is, if I understood correctly, you also looked at the selenium or sulfur vacancies, right?
Mm-hmm, correct.
And you showed these two features which are highly reactive.
Yes, 2 defect states.
Did you also look at the tungsten vacancies or tungsten defects?
We didn't see any tungsten vacancies in our samples. So the sulfur vacancies we can create by annealing. So this has the lowest formation energy. So that's the first thing to form. I think a tungsten vacancy or transition vacancy are much higher in energy, and we didn't see those. So they don't come naturally after the growth, and we couldn't induce them.
Okay. Thanks.
Sure.
Thank you very much for your questions. Is there any other question? Or okay, last chance. Okay, so then let's move to the next talk. Thank you very much, Bruno.
Thank you, Aaron.
So now we have another contributed talk. This time by if you can stop sharing, Bruno, then we can. Okay, now it's coming. We have the next contributed talk by Oreste De Luca, who's coming from Hi, good morning. Who's coming from the University of Groningen, and he'll be talking about photoluminescent on molybdenum disulfide. So please go ahead.
Thank you so much. Good morning to everybody. And first of all, I would like to thank you, organizer of the conference, for giving me the possibility to present this talk today. Today, I will show you some results regarding the photoilluminations of the molybdenum disulfide by surface functionalization. So the molybdenum disulfide belongs to the family of the transition metal chalcogenates, and TMD's monolayer are a very popular, let's say, family that is deeply studied today, and their atomical thin semiconductor, general formula MX2, where M is the transition metal and X is the chalcogen. And this family is studied in depth nowadays, and because is promising materials for several applications, including sensors, transistors, photodetectors, solar cells, and so on. The molybdenum disulfide is one of the most studied TMDs due to its unique chemical and physical properties. In particular, its high carrier mobility can be used to generate new electronic and optoelectronic devices, and conversely, the bulk MOS2, the monolayer MOS2 has a direct band gap, so it means that it has a strong photoluminescence at room temperature. The conventional synthesis mix of the molybdenum disulfide are essentially three: CVD, the chemical vapor deposition, the mechanical exfoliation, and the liquid exfoliation. The CVD is the most promising technique to synthesize MOS2, because it allows us to have large flakes of MOS2 at surface. But there is a big disadvantage, and the disadvantage is that the mobility in the CVD grown MOS2 is typically less than the mechanical exfoliated ones, and this is due to the presence of the defect. The defect, when we talk about the defect in MOS2, we usually refers to the monoatomic vacancies at surface. And one of the most common is sulfur vacancies at surface in MOS2. Sulfur vacancies has a big disadvantage. Surface is reduces the mobility of the molybdenum disulfide. So it means that we cannot use the molybdenum disulfide in applications. But there are, let's say, actually plenty of solution, and one solution is to covalent functionalize the molybdenum disulfide. So the idea is that if we have some vacancies at surface, we can fill the sulfur vacancies with a sulfur of a molecule covalently bonded to the MOS2. And in our work, we used molecules TCNQ and the ATTF that are respectively an electron acceptor and an electron donor molecules. So these molecules, the terminal part of these molecules consists of a anchoring sulfur group. So what we expect is that the molecule should bind to the molybdenum disulfide and should bind filling the intrinsic sulfur vacancies. And so in this way, the mobility of the MOS2 should increase, and so increasing also the illumination intensity. The samples are the TCNQ over MOS2 and the molybdenum disulfide grafted with ATTF. And our main goal was to demonstrate that the chemisorption of the molecules on the molybdenum disulfide can enhance the photoillumination. So the molybdenum disulfide was grown by the CBD. So in the figure at the center, you can see the schematic of the CBD tube. So it was grown in argon flow on silicon oxide. After the CBD grow, the molybdenum disulfide at surface is not uniform. In fact, we can distinguish at least 3 distinct regions: front, the middle, and the back one. The front is the region closest to the MO03 source. So the front one presents a full coverage of molybdenum disulfide. The middle one separated and also coalescing islands of molybdenum disulfide. The back one, small MS2 flakes. And regarding the thickness is the typical of a monolayer disulfide layer. So is a monatomic layer, sorry. So after the synthesis, the grafting by using these 2 molecules, the grafting was made in a simple way. So the freshly grown molybdenum disulfide was immersed in a TCNQ or ATTF solution for 1 hour. And then the samples were rinsed with ethanol and then dried in nitrogen flow. So after the functionalization, we essentially used the 3 technique in order to check 3 important points of our study. So the first one, we used the XPS in order to be sure that the molybdenum disulfide was functionalized by the molecules. And then, this is the most important part of our work, we checked the photoilluminations if the carrier mobility increased after the functionalization. And at the end, with Raman spectroscopy, we checked if the crystal quality of the MOS2 is preserved after the functionalization. So the first sample is the molybdenum disulfide grafted with the TCNQ. This is the XPS results, and as you can see, the XPS confirms it is successful molybdenum disulfide functionalization. In fact, after the grafting, there is a figure on your left. Top figure is the S-grown MOS2. The bottom is the molybdenum disulfide after the functionalization. And you see that there is, after the functionalization, there is a chemical shift of 0.5 eV towards higher kinetic energy. This confirms that there is a charge transfer between the molybdenum disulfide layer and the TCNQ molecules. In particular, also by taking a look to the feeds of the S-grown MOS2 into the TCNQ over and after grafting, sorry, you see that the S-grown MOS2 is fitted, the molybdenum liver is fitted by the doublet, the red one, the purple one, and the blue one. The red one represents the intrinsic molybdenum, is the molybdenum in the molybdenum disulfide. The purple one is the affected molybdenum, I mean, is representative of the molybdenum atoms close the sulfur vacancies. The blue one is the contamination of molybdenum that came from the unreacted MoO3. After the grafting, essentially, you see that the ratio in the red doublet and the purple doublet increases. So it means that the defect decreases, and so it means that let's say a lot of vacancies are of sulfur vacancies are filled by the TCNQ molecules. And also the sulfur P for liver region confirms that after the TCNQ functionalization, there is a chemical shift of let's say around 0.5 eV towards higher binding energy. For the graft for the molybdenum disulfide grafted with the ATTF molecules, it's easy to see that also in this case there is a functionalization. In fact, after grafting, there is a chemical shift of around of about 0.4 eV towards lower binding energy, and also in this case the molybdenum 6+ species is absent after the grafting, and most importantly, the defect, I mean the molybdenum associated to the defect decreases after functionalization. That confirms also in this case that a lot of vacancies are filled by the sulfur of the ATTF molecules. And also to the sulfur TOP core level confirms that after the functionalization there is a chemical shift. I mean that there is a charge transfer after the functionalization. So after the XPS analysis, we carried out a photoluminescence analysis in order to investigate the effect of the chemisorbent molecules on the optical properties on the MoS2. And here, from the photoluminescence is straightforward to see that the photolumination intensity increases by 7 orders of magnitude in the case of grafting with the TCNQ molecules. Conversely, after the ATTF grafting, KPL intensity is even lower than that for the S-grown molybdenum disulfide sample. Okay, at this point, sorry, in order to gain more information, we also fitted, we also carried out a fitting of those three photolumination spectra of the S-grown molybdenum disulfide, and after the TCNQ and ATTF grafting. And after fitting, it's frozen, no, it's working. After fitting, it's easy to see that from central figure into the from the central spectrum of the figure, it's easy to see that the S-grown MoS2 is dominated by the contribution of the A- trion peak, and this confirms the nature of the end of the nature of the CVD grown MoS2. After TCNQ functionalization, the purple peak that is representative of the A exciton increases a lot in intensity, while the A- trion peak decreases. This, from the photolumination side, confirms that there is a charge transfer between the molybdenum disulfide and the TCNQ. So it means that after the functionalization, the exciton screening is reduced. So there is a suppression after functionalization of the non-radiative ion combination. Conversely, to the TCNQ cases, in the case of ATTF grafting, the main contribution is again related to the A- trion component. So this means that electron transfer from the ATTF TTF to the MOS2 promotes the exciton screening. So there is essentially an enhancement of the non-radiative trion recombination. With the photoluminescence, we also checked that there is essentially no difference in terms of photolumination spectra between a freshly prepared functionalized molybdenum disulfide and an aged one. And this is very, very important because this confirms that the chemisorbate TCNQ molecule on the molybdenum disulfide act as a passivating layer. So it means that this molecule are able to protect the MOS2 from the air or also solvent contaminants. Okay, finally, we used the Raman investigation to confirm that the crystal structure of the molybdenum disulfide hasn't changed after the functionalization. In fact, Raman mode is associated with structural effect in MOS2 is absent after the functionalization. So in conclusion, we use the TCNQ and the ATTF molecules in order to covalently functionalize the molybdenum disulfide, and this was confirmed by the XPS analysis. The Raman spectroscopy confirmed also that the quality of the molybdenum disulfide is essentially the same after the grafting, but the most important part of the work is given by the photoluminescence results. In fact, in the case of the grafting with the TCNQ molecules, RPL intensity increases by 7 orders of magnitude. Conversely, in the ATTF grafting, the RPL intensity decreased due to the non-radiative trion combination. Our approach is interesting because is essentially it shows that an irreversible enhancing of the PL intensity of the molybdenum disulfide could pave the way for a robust optoelectronic application. It's important because it seems that after a covalent functionalization of the molybdenum disulfide, there is no degradation in the event of prolonged air or solvent exposure. Very briefly, I want to say thank you to my research in Groningen, in particular to the Professor Rudolph, and of course, thanks to all of you for your kind attention.
Okay, thank you very much, Oreste, for your nice talk. Is there any question from the audience? Don't be shy, even if I'm asking you to use your mic. Okay, I have a very naive question myself. So you are using these two different molecules, the TCNQ and ATTF, separately. What would happen if you co-deposit them? If you were using both? We have of any interest. I'm just very naive.
Okay, actually, we didn't try it, but I think is something that we can try actually, because actually we didn't try. We simply deposited, let's say, I'm going to say separately. Yes, but I think it's also interesting also to mix some different molecules in order to see what happens in the case of.
But is there anything you can preview or?
I mean, actually, our starting point was to use the TCNQ as an electron donor and electron acceptor, let's say, molecule. The TCNQ essentially gave us something because the PL intensity increases. And it was surprisingly at the beginning that the ATTF molecules, it gave essentially nothing. Yes, but actually, after fitting with the fits of the PL intensity, we understand why. Because that molecule, even if from the XPS, I mean, the molecule is at surface, is covalently bonded at surface, but the trion recombination had decreased a lot the photolumination intensity. So it essentially is not a good molecule. In the case of the TCNQ molecule, the presence of the Hessiano group allows us to increase the PL intensity.
So it's the same. Okay, thank you very much. So we have a question. Honor, I'm sorry, I don't know if this is your first name or your last name.
No.
Honor, please go ahead with your question.
Good.
So I would like to ask, hello, nice presentation. So I would like to ask what do you consider is the best method for the production of two-dimensional molybdenum disulfide?
Did you hear the question, Oreste? Oreste, yeah. Oreste de Luca?
Yeah. Can you repeat? Can you repeat, Honor? Sorry. Yes. Sorry, Honor. Sorry. I'm so sorry.
So what do you consider is the best method to produce two-dimensional MEOS2?
I think the best method is, the best method, in my opinion, the best method is the CVD, because in our lab, there are some PhDs, also me, that are involved into the synthesis of in general, of the transition metal, the chalcogenates by the CVD. I think is one of the best because allows us to obtain, let's say, large flakes of the materials.
And how large do you manage to get?
Can you repeat? Sorry, Honor.
How large were your biggest crystals that you produce?
Yeah, in lateral side, you mean? Yes. Lateral side is let's say around 0.1 millimeter.
Oh, that's pretty big.
Yeah.
That's pretty big. Thank you. Thank you very much.
Good.
Thank you very much, Oreste.
Thanks a lot, Aaron. Sorry for before. Thank you very much.
So now we can move on to the next talk, who will be given by Mahfouz Rahman. So please, if you can share your presentation now. Can you hear me? Okay, yeah, there you go. So good morning.
You can see my slides.
Yeah, we can see your slides. If you can use the slide mode. Okay, that we can also see your mouse and we can also see you. So, so it's all set. So let's go. Yeah, next talk is gonna be by Mahfouz Rahman. Kind of. Yeah, probably not too close. Who's coming from the Chemnitz University of Technology in Germany. And he will be talking about photoluminescence, in this case in a different transition metal dechalcogenide, in tungsten diselenide. So please go ahead, you have 15 minutes. Thanks.
Thank you very much. Good morning, everyone. First of all, I would like to thank the organizers to give me this opportunity to talk about our recent work. I'm Mahfouz Rahman, as it is mentioned, and I'm a postdoc in the Sun Group in Chemnitz. So in this work, we studied dark excitons in tungsten diselenide monolayers using both micro and nano photoluminescence, and more importantly, at room temperature. So this is the outline of my talk, in which sequence I'm going to speak about. So I will mostly focus on the photoluminescence characterizations of our sample, but also in one of the slides, I'll also show you the correlation between the nanophotoluminescence and also TP-enhanced spectroscopy, what we also studied. So let's start with the introduction of dark excitons. What is it and how it's formed? We all know that TMDCs are monolayer. In monolayer, TMDCs are direct bandgap semiconductors with a transition occurring at the corners of the hexagonal Brillouin zones. And due to the contribution of strong spin orbit coupling, we have a large valence band splitting, what you can see over here. And because of this valence band splitting, we also observe two distinct features known as A and B. But if you look at the conduction band, then the splitting is rather moderate, which is in the range of 50 millielectron volt. And because of this situation, we have two distinct situations here. In one case, we have the spins in one of the conduction band state is similar to the top of the valence band. Therefore, this is permitted, and that's why it's called bright exciton. But in another case, we have spin states in the conduction band state, which is opposite to the top of the valence band, and therefore this particular exciton is forbidden. Therefore, this is why this is called dark excitons, as you can also see here, is shown by X0 and XT. And interesting is that all the molybdenum-based chalcogenides, we have the lowest lying conduction band state is bright, and for the case of tungsten-based chalcogenides, that the lowest lying conduction band is dark, and therefore this particular material is quite interesting to study dark excitonic physics, which can open some new interesting applications in future. So one of the characteristics of these dark excitons is that they have this out-of-plane transition dipole, and therefore this is really challenging to probe them in conventional optical spectroscopy. Even though if you look at in recent literatures, you can find that several groups, they engineered the experimental configuration to study these dark excitons, though the efficiency of the radiative emission of dark excitons is quite low, and therefore most of the studies are done in cryogenic temperature. So what we did in our work is that we sandwiched this monolayer tungsten diselenide between the metal substrate and polydimethylsiloxane or PDMS nanopatches. We know that PDMS has a strong polar bond in the form of silicon oxygen, which can alter or change the dynamics of the probing molecules. And we also know that the TMDCs or tungsten diselenide has intrinsic defects, and we can also create defects when we are transferring these flakes during the mechanical exfoliation. And therefore, our hypothesis is that a combination of these defects with the PDMS and the metal substrate, we have a strong out-of-plane electric field acting on this tungsten diselenide, and therefore we are able to observe this dark excitons, which I'm now going to speak about in the following slides. So before that, I would also like to introduce a sample preparation, because this is one of the important part of the experiments. So this is the sample schematic, the general sample schematic in our sample. We prepared the metal substrate using thermal evaporation of gold or silver on silicon substrate, and the nominal thickness of the substrate is about 100 nanometer. And then the monolayer flake was transferred with the aid of PDMS using conventional dry transfer method. And we know that this during this transfer method, we can also transfer some PDMS residuals along with the 2D flake. And therefore, if we anneal, which we did in nitrogen atmosphere for 2 hours at 150 degrees Celsius, this PDMS residuals will start to accumulate centering around the defect sites. And then you will end up with similar to this nanopatches. And if you look at this scanning probe microscopic images here, so before annealing, if you look at the topography, FM topography image, we see a nice homogeneous flake, or top of the flake is nice homogeneous, but the corresponding surface potential image shows some heterogeneity, which also indicates that we have some PDMS residuals on top of it. But after annealing, we have a drastic change in the topography. Now we have this nanopatches forming all over the flake, which you can also see in the corresponding surface potential image as well. And the thickness of the monolayer flake, we also determined about 0.7 nanometer, which is the characteristics for the monolayer, or the nominal thickness for the monolayer tungsten diselenide. And then we also, one of the questions also came to our mind that if these nanopatches are really forming on top of the tungsten diselenide, or these are simply bubble creating at the gold or metal substrate. Sorry, so simply creating a bubbles at the gold or metal and the tungsten diselenide surface. We also did current imaging. So in this case, you see the topography image where we see these bright spots over here, which corresponding to these nanopatches. And if you look at the current image, we can see some area where we don't see any current at all. And now if we superimpose this current image on the AFM topography, you can see that there is a nice correlation between the AFM topography and current image, which tells us that on these bright spots, we do not observe any current. Since these PDMS nanopatches are insulating, therefore we should not expect any current, means that these bright spots are really forming on top of the tungsten diselenide flake or creating these nanopatches. And another thing also we also confirmed here is that these nanopatches are really originating from the nanopatches. We also did conventional XPS and also imaging XPS. So in this optical image, you can see two distinct flakes of tungsten selenide. And if you look at the conventional XPS spectra, together with the tungsten and selenium contribution, we can also see silicon contribution as well. And since the thickness of the gold is about 100 nanometer in this case, we should not, we can completely exclude the possibility of substrate contribution or the silicon contribution from the substrate. And therefore, to really understand from where the silicon is coming, we also took the XPS imaging. So in this case, what we did is we took a spectra, we took an image at individual spectral energy positions. So in this case, we have the whole spectral range of silicon with a 0.1 nano or 0.1 electron volt range, and then we created spectra, and then we at the end we bind together to create this nice spectra what you see over here. And here this is one particular image, XPS image shown, which was taken at 33 electron volt, which is corresponding to the tungsten 4F core level. And here in this case, so this is the same area where this optical within the optical image, and here you can see that this particular flake which is adjacent to the monolayer, and also we have a bulk flake, and these two flakes are shown in area 1 and 3, and area 2 is completely tungsten diselenide free gold surface. Now, if we take silicon spectra on 3 distinct different areas, you can see that on top of area 1 and area 3, we can see the contribution of the silicon 2s, whereas on top of gold, we don't see the silicon contribution. Means that these nanopatches, what we see over here, they are really formed because of the PDMS. So then I would like to start with the micro PL measurements. So in this case, in the right figure, you can see the photoluminescence spectra taken before annealing and after annealing, and the corresponding spatial map of the flake with the intensity and the peak position map. So if you look at the before annealing spectra, we have a nice PL single featured PL spectra, which is the corresponding characteristic of the monolayer tungsten selenide centered around 750 nanometer. And the corresponding spatial map also shows homogeneity over the whole flake. So over here before and after annealing, you can see nice homogeneous center. But after annealing, the spectra changed drastically. So one of the things is intensity decreased dramatically, which can be because of the annealing effect where we see a quenching of the PL. But more importantly, what we see is that there is appearance of at least more than one features in the spectra, and this can also be seen if we look at the intensity map, special map of the intensity and the peak position. You can see that the images are not homogeneous at all now. It shows a lot of heterogeneity. So in order to understand the details, or in order to look at in more details into these additional features, we took this spectra and then took the first order derivative of this PL spectra. And from the first order derivative, you can see that we can see at least 4 features in the spectra, which were also featured with the Voigt function over here. So the first feature around 750 is the bright exciton in tungsten diselenide. And then the second feature, which is 33 milli-electron volt shifted from the bright exciton. And this is the characteristic triune feature, bright triune feature in tungsten diselenide. Then we have the third feature, which is 47 milli-electron volt shifted from the bright exciton, and this is the typical value for the conduction band splitting, and hence this is the dark exciton feature of the tungsten diselenide. And then we have the fourth feature, which the energy difference between this feature and the bright triune feature is about 33 milli-electron volt, which is also in accordance. This is the dark triune, and this is in accordance with the literature as well. And additionally, we also observed consistently in all the samples, there one weak feature around 800 nanometer. So this particular feature, the origin is not completely known, but we think that this is most likely, since we know from the literature that if we have dark defects and these defects can become alive if we have dark excitons adjacent to it, and then they're simply trapped within this defect. So we also did further characterizations to really prove that these are the dark excitons. And first one is the laser power dependent study, and this was done at room temperature. So in TMDC monolayers, beside fundamental features, what we see, we can also observe, or in the literature, we can also see that we can also be able to see defect related excitons, and also we can also be able to observe bi-excitons. And in case of defect excitons, it is already known that with the increasing laser power, they will be saturated. And in case of bi-exciton, the relation between the laser power to the bi-exciton is quadratic, means that with the laser power, it would be squared up. So, and if you now look at this laser power intensity versus laser power dependent profile of this these both features, they are collinear, and the slope of this dark features is dark excitonic feature is quite a good agreement with the literature, what we also observed in this case, in our case. Then we also studied temperature dependent study, since we know that at low temperature, all the features become more sharp, and therefore we can then identify all the features more easily. So in this case, the PL spectra at 86K, we can see the bright exciton, which is also shown here by X0. And then the Tryon peak, we can also identify, which is separated by 31 milli-electron volt. And the next feature, what we also observe over here, this is the dark exciton, then energy separation is 45 milli-electron volt. And then the next feature, which is our X dark Tryon, and the energy separation between the dark Tryon and the bright Tryon is about 32 milli-electron volt, which is also a good agreement to the our room temperature photoluminescence measurements. Apart from that, we also observed few other features which simply vanished as the temperature increases. And then there is additional features which I also talked about in the previous slide, that we observed one weak feature on 800 nanometer. So we can also see this feature, and as the temperature increases, this feature is also stays alive together with the other features what we also observe in our room temperature PL measurements. Next, we also studied circular polarization dependent studies, since this is one of the important characterization method for TMDC monolayers. We know that TMDCs has certain valley polarization selectivity, and therefore if we excite these TMDC monolayers with a certain right hand or left hand circular polarization, and then collect them with the in both configurations, then one should expect stronger enhancement for the co-polarized excitation and collection configuration. And this is what we observe for the bright exciton and bright Tryon. However, for the case of dark excitons or dark excitonic emissions, we see an opposite trend. And this is interesting. And if you look at the literature, then you can find out. So there are two mechanisms for that. One is the intravalley scattering, where you can intravalley mechanism, where you can simply flip the spin states. And another one is the intervalley mechanism, where you can simply shift change the bright excitons by scattering. And in that case, you need assistance from, for example, phonons or impurities or defects or any other additional electrons or holes in this case. One of the mechanisms what also been explained here is that because of the intravalley scattering, we have bright excitons which are simply moving across the valley, and therefore we can observe this dark excitonic, we can observe this opposite higher intensity with the opposite polarization effect. Next, I would like to move to the nano-PL measurements at room temperature. So this is the schematic of the nano-PL measurements. In this case, we used a gold tip inside illumination geometry, and our excitation was 630 nanometer. And because of the electric field of the laser, excitation laser was in parallel to the tip long axis, we can create a strong electric field at the tip apex. And because of the strong electric field, we were able to observe we were able to get the local informations with a resolution less than, spatial resolution less than 10 nanometer. So bottom, you can see the TPL map, and with the corresponding FM topography, which shows nice correlation between each other. And the two representative spectra. So spectra one is the spectra taken, or it was averaged over this rectangular area, and is shown in this top panel. So here you can see the TPL spectra with three distinct features. So one is around 750. So one is around 750, and then we can also see one feature around 765, and then we have additional features, which is the dark excitons. If you look at the energy separations, then you can clearly see that the first one is the bright exciton, second one is the Tryon, and the third one is the dark excitons. And this is not surprising because we use a metal tip and a metal substrate, and combination of these two effects will create a strong electric field, out of plane electric field. And because of the strong outer plane electric field, we can also excite dark excitons at room temperature. This is also been demonstrated by Rashke's group very recently, as you can see in this example. However, once we look at the TPL spectra on top of the nanopatches, PDMS nanopatches, you can see that there is a dramatic change now. Now the spectral features are more or clearly visible and indicating that all the features what we have observed in previous our micro PL measurements are basically coming or confined within this nanopatches, as it is shown over here. In the next slide, in the set of experiments, we also wanted to look at if there is any relation between the TPL measurements or TPL's measurements with the TPL's enhanced spectra. So in this case, we took two different spectra. One is on top of gold, what is shown in this blue PL spectra, where we can see one single feature, and one is on top of nanopatches, where we can clearly see these additional features or the dark excitonic features. Now, if you look at the tear spectra, corresponding tear spectra, so the red one is on top of nanopatches, we can see that the overall spectral weight is shifted to the higher wave number, and this also exclude the possibility that these nanopatches can create some tensile strain, because if it is tensile strain, then one should expect the overall spectral weight of the tear spectra should move to the lower wave number. And now if we fit this to spectra taken on nanopatches and also on top of gold, if you look at clear, especially or focus on your your attention to this particular feature, which is the out of plane vibrational mode, this particular feature is especially sensitive to the defects. And if you look at the both spectral features, then this A1 mode is most strongly enhanced or has higher intensity in case of nanopatches compared to on top of gold, which also indicates us that the defect density under the nanopatches is stronger compared to the area on top of gold. And if you look at this tear spectra was averaged over this whole gold area, and this tear spectra on nanopatches was taken within this small area. And if you compare the area, then we can clearly see that the defect density is stronger on under the TPL under this PDMS nanopatches. So at the final step, what we did is we cleaned up these nanopatches to really confirm that these features are coming because of the confinement, because of the combined effect of the PDMS and the gold. So in this case, in the top in the top row.
Rahman, sorry to interrupt you, but you have one last minute.
Okay, sorry, I should speed up. So here, what we can see is that the PDMS nanopatches, which are corresponding to this TPL spectra, and then what we did is we also cleaned up the PDMS nanopatches, and therefore, what you can see is that the TPL spectra is now similar to the TPL spectra on top of gold, and this is also happening over here. That once it is cleaned up with the spectra become more symmetric to the on top of gold. So I will skip this slide and also this slide. I would like to thank my HLPH group members and also the collaborator, Professor Gimming, who has a very good important input to the theoretical input to this work, and also the DFG funding for the financial support. And thank you all.
Thank you very much for your nice talk. It was sorry to have
I'm a bit slow.
Getting too long, and we have to also think about the speakers that are coming after you. Okay, so we have time just for a short question from Andrés Castellano Gomez. Andrés, please go ahead.
Oh, okay. Can you hear me?
Yeah, I can hear
you.
Okay. Hi. I was wondering if you have tried to clean up the surface of the tungsten diselenide by brooming with an AFM tip in contact mode.
This is what we did. I mean, in this slide. So what in this case, what we did is, maybe I can put it the whole slide. So in this case, we used this tip under illumination and we scanned continuously. And what happened that we cleaned off these PDMS nanopatches. As you can see from column 1 to column 4, we can clean off almost all the nanopatches on PDMS nanopatches. And at the end, we have only these nanopatches, which has this PL spectra over here, and then all these TPL spectra, whatever shown over here, they fall back to the the similar TTL spectra on top of gold.
All right, thank you. Sorry that I missed it.
I mean, I was really hurrying at the in this stage because of my late work.
Thank you.
Okay, thank you very much. Unfortunately, we have to. Oh, Cesar Moreno is asking. Sorry. Cesar, just 30 seconds. Cesar, go
Okay,
on.
just quick question. What about the lifetime of the exciton? Do you expect to have different lifetime in the regions with the PDMS or without?
According to the literature, definitely the dark excitons have longer lifetime compared to the bright excitons. But we don't have this capacity to really study this lifetime of the dark excitons in this case. Okay. But definitely it would be really interesting to really study.
Okay, thanks.
Thank you, Cesar. Okay, so thank you very much. And let's now welcome the next speaker, Artem Kononov. Please, if you can share your screen with us. There you go.
Good morning. So, can you see my screen?
Yeah, we can see your screen. So here we have our next speaker, Artem Kononov, coming from the University of Basel. And he's going to talk about superconductivity and edge transport in Telluride. Okay, go ahead.
Yes. First, I would like to thank the organizer for inviting me here and thank all the people who joined my talk. So this work has been done in the University of Basel by this team of people, and we were lucky to be provided by the Crystal with our collaborators from United States and from Japan. And so what I would like to talk today is tungsten telluride. So it's a layered transitional digital coordinate material with a particular set of properties which makes it very interesting for topological superconductivity or for possible future application in quantum computation. So this set of properties consists of two parts. First, there is some non-trivial topological properties. So the bulk tungsten telluride is Weil semi-metal with a Fermi arc surface states. And then monolayer tungsten telluride is 2D topological insulator with a helical edge states. And then the second set of properties which are important for topological superconductivity is, well, superconductivity itself. And it turns out that under many conditions, tungsten telluride is actually becoming superconducting. So it's becoming superconducting under high pressure or under electron doping, or its monolayer can even be gate tunable into the superconducting state. So this combination of non-trivial topology and superconductivity makes it very promising material. And in my talk, I would like to maybe persuade you that maybe there is even more to it. So there is probably also higher order topological insulator state in tungsten telluride with a helical hinge states on the edges of the crystals. And maybe there is also a flat band superconductivity at the interface with some metals. So let's start with our experimental results. First, we made a very simple device with in a whole bar shape with a thin tungsten telluride stripe shade flake. It's approximately 7 layers thick, and we studied our usual magnetoresistance characteristics. And so at 4 kelvins, we are seeing that there is this parabolic non-saturating magnetoresistance, which is a specific feature of tungsten telluride, and this suggests that the crystals we are using are of high quality here. Then we decreased the temperature and repeated the same measurements again. And this was the point where we found out that there is something interesting happening. So first, at higher magnetic field, there are Shubnikov-Degas oscillations, which are also suggest that the crystal is of high quality. So despite the low thickness, the mobility is at least 2000. The mean free path is at least 40 nanometers. But what is most striking here, we can see that at low temperature, at low magnetic field, there are two other states appearing in the magnetic resistance measurements. So we've done a number of experiments in different type of devices, and we came to the conclusion that actually these two transitions which we are seeing here, so the first transition is the formation of superconductivity on top of the leads in the sample, and then the transition to zero resistance state is the Josephson effect between the superconducting regions. And what is interesting that this Josephson effect is observed over quite high distances in micrometers range. So this initial observation led us to two questions. So we wanted to find out what is carrying Josephson current over such long distances in our cases. And second, like what can we find out in transport measurements about the superconducting state we are observing there. So to answer the first question, we made some new samples. This is again fuel layer thick tungsten telluride on top of palladium leads. It's covered with HBN. And we tried to exploit sensitivity of the Josephson effect to the distribution of current within the sample. So more specifically, we measured the dependence of the critical current on the magnetic fields perpendicular to the Josephson junction. And so one can think that these dependencies are analogous to optical experiments. So if the current is uniformly distributed throughout the width of the junction, then this is analogous to Fraunhofer diffraction on a single slit in optics. And there is this characteristic Fraunhofer pattern which decays quite quickly. And if there are only two edge states, then this critical current looks as a interference pattern with two slits, and such pattern called a squid critical current pattern. And actually, the connection between the critical current and the current distribution is given by something similar to Fourier transform, and one can actually deduce current distribution within the sample from measurements of critical current versus magnetic field. So this is the experiment we've done. Here is the measured dependence of the critical current on the magnetic field piercing through the junction. And we can see that there are many oscillations here. So we have this squid-like pattern indicating that there are some edge states, and by the robustness of this pattern, these edge states should be very narrow. So when we did Fourier transform, we actually find out that, yeah, there are indeed edge states, and they are below 75 nanometers wide. So to further try to understand what is happening here, we also looked at the symmetry of the supercurrent in our sample. And we found that this symmetry is actually quite different from what is usually expected in Josephson effect. More specifically, when the current direction is reversed or magnetic field direction is reversed, there is no symmetry. However, if both current and magnetic field direction are reversed, there is a symmetry preserved. And so basically, this observation corresponds to the predicted asymmetric Josephson effect. And two requirements to observe this asymmetric Josephson effect is the non-sinusoidal current phase relation of the edge states and asymmetry in the current distribution. So we ran some similar experiments on the number of devices. We also tried to have these experiments in devices with the steps, and we also observed that there are such states on the steps with a different thickness of tungsten telluride. And this led us to the conclusion that this Josephson effect is likely hosted by some topological states, and it is very likely that these topological states are hinge states of higher order topological insulator. So now, returning to our second question, what can we find about superconducting state, which we observed? So we again return to this whole bar device and measurements of magnetoresistance. So we repeated the measurements I showed initially in different temperatures, and we extracted the perpendicular critical field versus temperature. And what we found out that this critical field versus temperature perfectly follows 2D Ginzburg-Landau equation. And by fitting this equation, we found that this would correspond to a coherence length of 14 nanometers in the superconductivity in our samples. And so, as I mentioned before, the samples are of high quality, so we can be sure that we are not in a dirty limit, so we are more likely in a clean limit of superconductivity. And in the clean limit of superconductivity, knowing the superconducting gap and the coherence length, we can estimate the Fermi velocity. And it turned out that actually the Fermi velocity is surprisingly small. It's at least an order of magnitude smaller than usual Fermi velocity in tungsten telluride reported in previous experiments. Then to further understand properties of superconductivity, we tried to measure London penetration depth in our device. So usually for measuring London penetration depth, people are using radio frequency techniques, but in our case, we could try to exploit the presence of this squid-like oscillating pattern to estimate London penetration depth. And the idea behind it is when we have a Josephson junction, we put it in magnetic field, we obtain this squid-like oscillating pattern. The period of the oscillations is given not only by the flux through the geometrical size of the Josephson junction, but rather by effective area of the Josephson junction, which includes length of the junction and penetration depth of the Josephson junction. So by comparing the period of oscillations with the geometrical size of our Josephson junction, we obtained that penetration depth in our case is around 400 nanometers. But the only catch here that this is not actually a London penetration depth, because we have a very thin superconductor, which is around 5 nanometers thick. And for a thin superconductor, to obtain London penetration depth, one needs to use this expression for Pearl's penetration length. So using this expression, we obtained London penetration depth is 50 nanometers in our material. And this is surprisingly low value for a semi-metal. And so this low value of the London penetration depth basically suggests that there is a huge concentration of superconducting carriers in this superconductor. And it has a further implication that since there are many superconducting carriers, this means that there is a very high density of states at the Fermi level in our superconductor. So basically both these observation that there is a high density of states at the Fermi level and there is at least an order of magnitude smaller than usual Fermi velocity suggest that maybe superconductivity in our sample is of flat band origin. And so we tried to understand a bit what could be the reason for this superconductivity in our sample. And we think that there are two main possible contributions to this flat band superconductivity. It's either strain at the interface with palladium or electronic doping from the palladium. And to maybe try to somehow guess which of them is more likely, we've done additional experiments with the in-plane magnetic field. We measured critical in-plane field versus temperature, and what we found that in-plane critical field in our superconductivity exceeds by a factor of 3 at least the superconductivity Pauli limit for superconductivity. And so this can provide some valuable insight into origin of the superconductivity, because, for example, in case of strain at the interface, we probably expect some phase transition similar to pressure-induced superconductivity. And in pressure-induced superconductivity, the critical field was below the Pauli limit. On the other hand, if this effect is due to doping, we probably expect something similar to the doped tungsten telluride sample. And in this sample, indeed, the in-plane critical field was exceeding the Pauli limit for superconductivity. So we think that doping is probably a dominating factor for this superconductivity we are observing in our samples. And so to conclude, I tried to show you our results about edge transport in tungsten telluride due to high order topology and flat band superconductivity in tungsten telluride and the interface with the normal metal. Thank you for your attention.
Thank you very much, Artem, for your very nice talk. Is there any question from the audience? Okay, we have Cesar Moreno, who's wanting to ask something.
Okay, thanks for your talk. I would like to ask you about the mechanism or behind the break of the superconductivity with the magnetic field. Do you expect to have some vortex or something, or some vortex spinning related with this palladium defect or this kind of things?
You mean in perpendicular magnetic field, or?
Yeah.
Well, I mean, yeah, it's not clear what the mechanism of breaking superconductivity is, but probably we would expect some vortices since the ratio of London penetration depth and coherence length suggests type 2 superconductivity in our case.
Okay, so somehow that works like the YBCO, this kind of superconductors, or this kind of 2D superconductor. I mean, yeah. Maybe if you can control the vortex spinning, you can improve your critical field, right?
Well, yeah. I mean, this we could probably try.
Okay, thanks.
Thank you for your question.
Okay, is there any other question? People are getting very shy this morning. Okay, so if there are no further questions, then we'll thank Artem Kononov again and welcome the next speaker. Thank you very much.
Thanks. Bye.
Okay. And, so our next speaker is a local speaker from Madrid, Victor Marzoa. So please, if you can share your screen. Okay, we can see it. Nice.
Okay, good morning. I don't know how to put the mouse, the pointer, sorry. Because it should appear here like tools or something, right?
Yeah, it usually does. If you move your pointer upwards, well, that's how it works in my computer at least. And then now I can see your mouse at least.
Okay, but not the pointer, the red pointer.
Do you have two screens or one screen?
One screen.
Okay, normally you have one screen where you see this presentation, and then there is another one.
Yeah.
If you put another one there, you normally see. Otherwise, if you go top.
If you go upward, if you go to the top of your screen, usually it comes up all the tools from Zoom. That's how it works on my computer at least.
Okay.
If not, I mean, we can see your mouse, and that's.
Okay, well, I'll try to do it with the mouse then, because I cannot see it. The tools.
I think it's good enough like this.
Also,
okay,
I think that when it shows the arrow instead of the pointer, it's because you have shared your full screen instead of just a presentation, maybe.
Okay, so. Okay. Screen. Well, I don't know. Well,
but in any case, the arrow works as well. So.
Yeah, so let's do it with the arrow. Okay.
Okay, so let's welcome Victor Marzoa.
Thank you very much, Sara.
INDEA Nanociencia in Madrid, and he's going to be talking about the optical characterization of molybdenum disulfide mechanical resonators. So please go ahead. Thanks for joining.
That's right. Thank you very much. First of all, I want to thank the committee and the organizers for the opportunity to present my work that I'm carrying out as a PhD student at INDEA Nanoscience in Madrid under the supervision of Professor Daniel Granados and Dr. Ramon Bernardo Gavito. And I'm going to talk about the optical characterization of few layer molybdenum disulfide mechanical resonators. So in the outline of this talk, I'm going to lay out the background needed to understand our proposal for the project, then the methodology of how we fabricate the samples, and the results of the optical characterizations, followed by the conclusions. So first, I will start with the background. Since the isolation of graphene for the first time in 2014, 2D materials have drawn the attention of the scientific community due to their amazing properties, and they have been used in many applications from electronics, optics, quantum technologies, biotechnologies, etc. From insulators to superconductors, 2D materials offer a wide variety of states, and today we're going to focus on those that have a band gap, the semiconductors, for example, molybdenum disulfide or tungsten diselenide, that have a band gap between 1 or 2 electron volts. And these are interesting because they can be tuned their optical properties. So in particular, molybdenum disulfide, it's very interesting because its band gap is within the visible spectrum. It's very easy to exfoliate, widely available, and very well known. As we've seen in the previous talks, we all talk about this material. So this is an ideal material for our mechanical resonators. The molybdenum disulfide belongs to the transition metal dichloroglycinide family, and it has a layer structure of sulfur and molybdenum layered planes separated by 0.65 nanometers. And they have a band gap that depends on the number of stack layers. So their band structure depends on the number of layers. So for it would be a direct direct band gap in the case of monolayer, or indirect for more than one layers. So this is going to affect to the optical emission of or optical properties of the molybdenum disulfide. And as you can see in this plot, photoluminescence is represented as a function of the wavelength. It can also be represented as a function of the energy. And as you can see here in these curves, it's represented for a monolayer, a bilayer, and few layer and bulk material. So the thinner the material is, the more photoluminescence it has, because the band structure is changing. It has a transition from indirect to direct. So this is going to increase the photoluminescence, as you can see. And we have two characteristic excitonic transitions of this material that are exciton A and B. That is due to the spin orbit coupling that arise from heavy transition metals that lead to the splitting of the valence band. So another important property of molybdenum disulfide is that its Raman modes, the two characteristic Raman modes, E and A, the out of plane vibration and in plane vibration, the separation between them also depends on the number of stack layers. So it becomes closer together with the decreasing number of layers. So this makes Raman spectroscopy an ideal tool to layer identification, and we are going to use it in our samples to identify the number of layers. So recent studies, this is the motivation. Recent studies have shown the potential, the high capabilities of transition metal dichloroglycinides to being used as in strain engineering applications. So in this paper, suspended or tungsten diselenide membranes suspended onto nanopillars were fabricated to create single photon emitters. They transferred the bidimensional material onto these nanopillars, and due to the strain that the nanopillars induced to the membrane, the band gap energy changes locally, and the photo emission, they observed that it had a higher photo emission in the areas where the nanopillars were situated. And this effect was higher for a bilayer than for one monolayer. So in our project, we want to take this idea, but instead of having nanopillars, we want to take advantage of the resonant modes of a suspended circular membrane. So we want to oscillate the membrane by applying a backgate contact and create these modes to induce the strain in the material. And the strain caused by this periodical deformation of the lattice, we think would be sufficient to modify the band gap energy, just like the case of the nanopillars, and modify and increase the optical emission in these areas. So this is our goal. And now I'm going to talk about the methodology, how we fabricated the samples, and then the optical characterizations. So the samples were fabricated in the Center for Nanofabrication at IMDEA Nanociencia, using different methods that I will explain in following slides. And we fabricated 2 types of samples. One where the flakes are suspended without the contacts, and the other one with the contacts in order to later on oscillate the membranes. So the first step of sample fabrication, we have the initial wafer, silicon wafer. The first step would be to deposit the resist by spin coating. Now the resist is a dyed material that when it's exposed to UV light or a high energy light, it varies its solubility to developer. So in our case, we use positive photoresist so that when we expose to UV light, it's more soluble to the dedicated developer. And we transfer this pattern here that it's shown in the screen, where the red spots represent the holes that we are going to etch later on. And we have different sizes for these holes, from 7 to 3 microns. And then the blue numbers are just is a pre-pattern that helps us locate the devices in our sample. So the second step of sample fabrication is to etch away the silicon to create these holes. So we use sulfur hexafluoride and fluoroform at room temperature, and we etch away the silicon in the open areas, and we dig as deep as 2 or 3 microns. And this is the picture of before the etching process. Now, the last process would be to exfoliate. We use PDMS to exfoliate the flakes and then transfer to the silicon substrate to deterministically transfer. So we have a flake that we think it's thin enough, and we transfer it onto the hole in any hole that we want. And this is the result, the flake suspended onto the hole in the silicon substrate. So now that I have explained the fabrication process, let me explain the results of the optical properties. So in this first flake I want to show you, it has different areas with different thicknesses, as the Raman spectroscopy showed. We have 1 layer, 2 layer, 3 layer, and bulk. And as you can see, and I said before, that the Raman peaks come closer together with the decreasing number of layers. And this also in the PL intensity has an effect, so that the thinner the flake is, the more photo emission that it has in general. So the blue one is the 1 layer, and it has higher photoluminescence. So this is at room temperature. And now what happens when we cool the flake? So we cool the flake, we cool down the flake using a cryostat down to 4K. And what happens is that we observe that the intensity of the PL, it's much higher. Notice that it's an order of magnitude or even more than at room temperature. This is 100 and this is 10. And the second thing is that we have a shift in the energy to higher values, what it's known as a blue shift with the PL in general. And also new peaks are revealed. So it's easier to identify. Here there's actually, instead of 1 peak, we can see there is 2 components of this peak, and we're going to study this. And also there is one here at around 1.8 electron volts that I will explain. So the first thing, why do we have a blue shift? Well, this was explained back in the late 1960s by Barsny, and he proposed this experimental equation where he related the bandgap energy of a semiconductor with the temperature. The study was done with traditional semiconductors, but it can also be applied to transition metal decalcogenides. So when we cool down a semiconductor like silicon, or in our case, molybdenum disulfide, its band gap energy increases, and therefore the blue shift. It's hard. It requires more energy to recombine an exciton. So that's why, and also you can see in the plots that the photoluminescence increases and it has a blue shift. Now, the second thing I wanted to tell you is that even though at room temperature looks like we only have one peak on the PL, it actually it's composed of two peaks, and we can see this better at 83 Kelvin, for example, or low temperature. And this second peak, one is the exciton, and the second one is the tryon. So it's which consists on it's a negatively charged tryon, which consists on 2 electrons and 1 hole, bound together by the Coulomb interaction. And they are very close together and have very similar values similar energy values that depend on the energy. And for example, in this case, they applied a gate voltage to look at the dynamics of the tryon and exciton. And the other peak that I told you, it's the 1.8 electron volts. According to some literature, it could be associated to sulfur vacancy, and it's a defect peak that can be observed at low temperatures. So now that we have identified all the peaks of the PL and we have the energies values, now let's look at the suspended part of the flake. So here, this is an optical image in the microscope of this area, and here is the PL map of the material of the flake, and this is the line scan. So we cut scan through or along this direction of the flake, and let's look here at the graph. So the green zone is the fringe standing, and the first thing that we observe it's that the PL decreases its intensity right in the center on the green. And what is even more interesting is that around the edge of the hole, there is a red shift towards the tryon, the value of the tryon, and the energy looks like it's higher. Sorry, the PL intensity looks like it's higher. And this is in the PL map, we can see tryon A that the photoluminescence is higher at the edge of the hole. And if we cool down the sample, we see the same, that in the center or in the middle of the hole, the PL is quite low actually, but in comparison with the supported area, which is much higher. And we observe also a little bit of shift. We believe is due to strain, according to most literature. And we have repeated this same experiment, and it's reproducible. Here you can also see again the red shift towards the exciton, towards the tryon, and the same with low temperature. So now I'm going to explain the optical characterizations of the flakes, but this time suspended onto the gold contacts. Like in this picture here, we're going to deposit the flakes onto the contact. This is the contact, and in the future we will apply a gate voltage in order to oscillate the membrane. So these are the samples that we have fabricated. With this white area is the gold contact, and in the center are the holes, and on top is the flake, the few layer molybdenum disulfide flakes. So this one, for example, if we compare the spectra of the red point with the green point, this one is inside the hole, and this one it's outside. The red one is shifted it's red shifted towards the value of the tryon. So this could also be due to the strain of the material, because in the middle is a strain. And also the B exciton is also shifted to the left, sorry, well, to lower energy values. And P3 is just the background noise of the gold. So and this was taken using with a with a blue laser.
Sorry, Victor.
Yeah.
Just 1 minute. You are running very late. Okay.
Okay. Okay. So in this other flake, you can see that at the edge of the hole, the PL intensity is much higher, and you can see on the maps that it's higher at the edge, and you can also see a little bit of the shift. And when we cool down the sample, it also appears another peak here, which is the D peak, and it increases the PL intensity. So to conclude, we have compared suspended membranes at room temperature and 4K. We observe a higher photoluminescence values at the edge of the holes, probably due to strain. And in the future, we would like to oscillate the membrane to induce this strain in the middle of the hole and create these quantum confined regions that could be used with high technological interest, and further study the exciton and tryon dynamics. And I want to thank all the sponsors and my colleagues in Indea Nanoscience, and thank you all for your kind attention.
Okay, thank you very much, Victor. We have time for one short question. Please, Andrés Castellanos Gomez, go ahead.
Hi. Yes, my question is if you have calculated the amount of maximum strain you are expecting from the mechanical resonance.
Hi, thank you, Andres, for your question. We haven't yet calculated how much strain is going to experience the suspended flake. We know by the literature that it's that we have to use megahertz to resonate these membranes, because the resonant modes are in the order of megahertz, and the strength that they're going to experience, we don't know it yet. So, I mean, we are very excited to do it. So there's like experimental work that we need to do, but also like to prepare the experiment and study how it's going to affect the resonant modes. I don't know if I responded correctly, but
yeah,
thank you.
Thank you very much, Victor.
Yeah.
So now we should keep moving and going for the last talk of the session. So the last speaker is Nacho Martinez. So if you can please share your screen.
Yeah, I'm on that now. Let me check a bit. So, wait 2 seconds. Now, is it working?
Yeah, sure. So welcome, Nacho Martinez. He's another local speaker from ICEM in and he's going to be talking about cathode luminescence in tungsten diselenide nanotubes. Disulfur.
Okay.
Disulfur nanotubes. Go ahead.
Thank you very much, Sarah, for the nice introduction, and hello, everyone. So thank you very much for this opportunity of presenting this recent study, combined experimental and theoretical, on cathodoluminescence in single and multi-wall tungsten disulfide nanotubes. I would like to thank to the partners in the project, in particular to the experimental branch, Professor Al-Azak, Professor Volker Bruser, and Dr. Ronit Popovits-Bairo, and in particular to my thesis supervisor, Professor Julio Afonso Alonso. The outline of my talk will consist in a brief introduction with the motivations and main goals of the project. After that, I will speak about the experiments carried on in this kind of nanotubes, passing to the theoretical calculations and modeling of these systems to finally pass to the final conclusions. So it's very well known that the electronic properties of layered TMD nanostructures are very closely related to their morphology, if they are planar or spherical or tubular, their size, the number of layers, and in the case of nanotubes, to their chirality. The classic example is the indirect to direct band gap transition by exfoliating the bulk of these materials to a monolayer. So the energy gap of the indirect transition increases as the number of layers decreases, and it can be attributed to a quantum size effect, even achieving the direct band gap semiconductor in the few layers limit. So this induces a dramatic enhancement of the luminescence quantum efficiency and permits the treatment of these systems and using these systems for a plethora of optoelectronic applications, including switchable electronics. But is this happening for TMD nanostructured versions? For example, in the case of the zero-dimensional nanoparticles, in the case of the tungsten disulfide nanoparticles, the layers are bent into cospheres, creating onion-like configurations, but they retain the structure inherent to the bulk. For example, regarding the optical properties, in nanoparticles with less than 5 external layers, the A and B exciton energies experiment a blue shift with respect to the bulk, but with nanoparticles with 6 or more external layers, this effect turns in the opposite, and the blue shift turns into a red shift. This is not very well understood up to the date, but it could be due to deformations, curvature, and discommiseration between the layers forming the nanoparticle. In the case of the nanotubes, the layers are bent into coaxial cylinders, and a shrinkage gap effect can be observed in these nanotubes. For example, the A exciton transition energy for the case of multi-wall tungsten disulfide nanotubes is at 198 electron volts, which is lower than the bulk, and it becomes smaller with a decreasing nanotube diameter. It has been characterized with Raman experiments. Nonetheless, the band gap of these single wall nanotubes, for example, for the molybdenum disulfide or the tungsten disulfide, has been investigated just by theoretical studies. It's for that the main goals of this project is taking advantage of a highly specific and a highly controlled protocol to synthesize single a few layers transition metal decalcogenide inorganic nanotubes. And in the present case, we are going to focus in the tungsten disulfide to get benefit of band gap engineering towards optoelectronic applications, for example, of this indirect to direct band gap transition by using the cathodoluminescence technique. It will be also interesting using first principle frameworks to rationalize these results, trying to get interesting predictive trends. So regarding the experimental synthesis of these nanotubes, I would like to emphasize that it's difficult, the synthesis of the single wall nanotubes of this material, because the small diameter nanotubes accumulate a large amount of strain energy. So just to compare, 1 order of magnitude with respect to carbon nanotubes of the same diameter, is for that we need highly energetic conditions. For example, high energy plasma to create large amounts of these materials and being able to tune the optical and band gap properties. And of course, such a protocol would open the door to a large bunch of applications and to a bandgap engineering versus the dimension and the chirality of the systems. The experimental branch of the project has developed a novel protocol to create these small nanotubes, single-wall and multi-wall nanotubes, starting from multi-wall nanotubes of tungsten disulfide. So starting with multi-wall nanotubes, synthesized with a very poor control by reduction and evaporation of tungsten oxide, plus a process of sulfurization. After the creation of this parent multi-wall nanotube, argon plasma irradiation is able to cut fragments from the external layers of this nanotube along specific crystallographic directions. This is a very, very nice advantage because one can more or less select the chirality of the nanotube being obtained. And once the plasma cut the fragment, it immediately falls in the opposite direction, releasing the large elastic strain stored. So the dangling bonds of the piece cut, trying to roll over itself, creates a bunch of a large variety of different small nanotubes. So by this methodology, we can produce nanotubes with between 1 and 5 layers, with 3 and 7 nanometers of diameter and up to 100 nanometers length. You can see the process in the figures shown in the slide. So in the characterization of this process, here we can see 3 pictures. The A and B are SIM images of the conglomerate of parent nanotubes. And in the C picture, we can see after they agglomerate and disperse the different nanotubes in an acetone solution, one multi-wall nanotube with 24 layers and 56 nanometer diameters. We can see also an optical picture of this nanotube. So we can obtain by this methodology, for example, nanotubes like this, single wall, or multi-wall like this we're seeing. Even it's possible to appreciate the process of the rolling of the layers towards the formation of the multi-wall nanotubes. And it's interesting also that we have performed XPS experiments in the pristine multi-wall parent nanotubes and after the plasma treatment, and we can observe that the peaks maintain the binding energy, which means that we are seeing obviously the tungsten disulfide nanotubes before and after, and we observe a small reduction of the, a large reduction of the signal that could be attributed to the dilution of atoms on the surface the nanotubes are sustained. So all this pre-characterization just to perform cathodoluminescence experiments on these nanotubes. And just for remind you what is the cathodoluminescence. The cathodoluminescence is the process whereby the light is generated when an electron beam hits a luminescent specimen. So the wavelengths of the light generated is in the range between the ultraviolet and the infrared, and the luminescence can occur in these tubes when with a direct band gap, an electron in the conduction band recombines with a hole in the valence bands by emitting a photon. So to perform these experiments on cathodoluminescence, first we have analyzed the spectrum of UV visible to see regions where the dispersion is good and is good, and the spectrum of the UV and visible spectrum is clearer, just to perform the cathodoluminescence sessions. And here we have 3 different regions. For example, in the upper panel, we can see a region with just with no single wall nanotubes and with the first faults created. A second region with multi-wall nanotubes, and the last region just in the bottom part of the slides just containing single wall nanotubes. And what we can see from the spectra is that when passing from multi-wall nanotubes to the single wall nanotubes, we observe a blue shift in the main peak of the spectra, which is attributed to the main transition. So in this case, the blue shift is of 0.11 electron volts, and it's mainly due to the quantum confinement along the z-axis of the perpendicular to the layers. And it's interesting also that if we compare the value obtained for the single wall nanotubes of 198, we can compare with the value of the book, which has been measured between 2.01 and 2.05, which also shows a blue shift. So with these results, we can complete the scenario for these materials. And here in the picture, we can see the evolution of the systems with the strain energy and the evolution of the systems with the value of the band gaps. And we have the full panorama and the full scenario to select the system with the desired functionality where we are interested in. So in order to rationalize these results, we have carried out a large battery of first principle calculations, both static, in order to get the static properties of the systems, and also photoexcitation spectra to compare with the cathodoluminescence results. So we have characterized a large bunch of systems comprising armchair nanotubes of different sizes, zigzag nanotubes of different sizes, and combinations to create double wall nanotubes. And we have also analyzed different planar structures between the comprising the monolayer, bilayer, trilayer, and also the bulk. So the static properties of these systems, in this picture, we can see the relation between the electronic gap and the nanotube diameter. We can see that the electronic band gap decreases steeply as the nanotube diameter is reduced. But which is more interesting is that when we analyze the gap of the double wall nanotubes we have formed theoretically, the electronic gap is in between the band gap of the isolated nanotubes forming the double wall, as you can see in the zigzag nanotubes, and in the one, as an example, in the armchair nanotube. And regarding the strain energy, we can observe that if we analyze by separate the zigzag and the armchair nanotubes, we can observe a difference in the strain energy between the zigzag and the armchair nanotubes is tiny but distinct. I mean, the zigzag nanotubes are unambiguously more stable than the armchair nanotubes, and the difference goes from 72 millielectron volts to 7, going to saturate up to the value of the molar layer. And it's interesting also that the results reproduce the 1 divided by the value of the diameter square as predicted for other nanotubes, like the case of the molybdenum disulfide nanotubes. So in principle, according to these results, the cathodoluminescence results should be compared with the zigzag nanotubes, are slightly more stable than the armchair, but this is also confirmed if we compare the static properties of these nanotubes with the experimental values of the gaps obtained in the cathodoluminescence spectra. I remind you that the value of the blue shift between the multi-wall and the single wall was of 0.11 electron volts. And if we show this trend from the theoretical calculations, we can see that between the 16.0, 28.0, and the 28.0, we observe a blue shift of 0.45 electron volts. The same occurs, but with a reduced value between the other double wall nanotube tested. And this blue shift is also observed not only for these two zigzag nanotubes, but also for the armchair one. And as you can see, as the diameter of the nanotube increases, the value of the blue shift decreases tending to the experimental value. Nonetheless, it's well known that the standard DFT does not provide a great description of the excited electronic states. It's for that we have performed time-dependent DFT calculations in order to improve a bit the description of the excited states. Unfortunately, it's not possible to go to more accurate techniques, for example, GW plus the Bethe-Salpeter equation, because some of the systems become very large, and one of the purposes of this project was the comparison between them. So here we can see the calculated photoabsorption spectra obtained by TDFT, and we can see that the spectra are very rich in features, and it has been calculated for the zigzag nanotubes, armchair nanotubes, for some planar structures. For the single wall zigzag nanotubes, we can see absorption thresholds ranging between 1.69 and 214 electron volts. And it's interesting to notice that the three largest nanotubes are consistent with the cathodoluminescence gap of 1.98 electron volts. So the blue shift is evident with respect to with the double wall nanotube in the case of the zigzag nanotubes. So yes, in the case of the single wall armchair nanotubes, the absorption thresholds are above 2.7 electron volts, which is far from the experimental results. Nonetheless, it's also possible to appreciate this blue shift with respect to the double wall nanotube. And finally, the planar structures shows thresholds of 3, 2.37, 2.27, and 2.12 for the bulk, to be compared with the previously measured bulk gap of 2.01 and 2.05 given in this reference. So the agreement is good. And just to conclude, it's also possible to find a red shift in the absorption thresholds of both double and single wall nanotubes, except for the case of the tube 520, which is a bit higher than the book, but this could be attributed to the differences induced by the temperature, which is not accounted in the calculation. So in general, we can see a nice agreement with the experimental gaps obtained from the cathodoluminescence experiments. So, and just to conclude, so the experimental branch of the project has developed a very highly specific and highly controlled protocol to synthesize single and few layer nanotubes. They have used the same TEM optical XPS and UV visible characterization to pre-optimize the cathodoluminescence experiments. From these experiments of cathodoluminescence, it's possible to appreciate a blue shift in the single wall nanotubes with respect to the multi-wall, and even a red shift in the single wall with respect to the bulk. So we have also used the first principles calculations to characterize the structure and electronic properties and photoabsorption spectrum of these systems with very nice results. And to conclude, I will say that this study opens the door to band gap engineering in these nanostructures towards the use in a large variety of applications. Thank you very much.
Okay, thank you very much, Nacho, for the nice talk. Is there any question in the audience? Oh, I'm trying to see myself. Well, I have a couple of questions myself.
Okay.
First, you have done these DFT calculations for the armchair and zigzag nanotubes, but maybe I didn't get it, or just because I'm not an expert. But can they control what kind of, if they have zigzag or armchair? This is not controllable in the experiments?
In principle, yes, in principle. I mean, one of the advantages of the methodology is that they can apply the plasma beam in the direction they want, and in principle, it would be possible. The thing is that the closing of the nanotube, if it's so evident, like in the other cases of classical chiralities, but in principle, you can control the chirality of the nanotube.
Okay, because you were comparing your DFT calculations for Amchar and zigzag with experimental ones, but I didn't see any, or maybe I missed it. I didn't see you giving experimental numbers for Amchar and zigzag.
No, actually, most of the experimental, 99% are zigzag nanotubes.
Okay.
Are zigzag nanotubes.
And also in the theory, you are considering single and double.
Yes.
Wall nanotubes.
Yes.
When you say in the experiment that they have multi-wall, what does this mean? They have double?
No, actually, they have mostly 3-layer, but they can reach up to 5-layer multi-wall nanotubes. But the number is 3, the most typical. But in theory, it's very difficult to reach more than 3 layers, at least with this methodology, you know.
No, because I mean, the DFT results that you are giving are, I mean, there is like a trend, obviously, but we know there is always this, limitations with DFT with regard to gaps. So yes. If you are not comparing exactly the same experimental structure and you are not comparing with exactly the same number of layers,
no, probably not. Probably not. I mean, but it's important for us in this case just the trend to see that the blue shift is given between the single wall and the double wall, which is the maximum number of layer nanotubes we have checked.
No, because you were being quite specific about the numbers. I think you can probably trust the trend, but
yeah, you can trust the trend, exactly.
I would be a little bit careful.
Yeah. You're right.
Okay, if there is someone else who wants to ask anything now before we take the picture, so don't run for lunch. I know we are all a little bit tired already, but okay, so it seems there are no more questions. So thank you very much, Nacho Martinez. And with this, we close the second session of this physics in 2D nanoarchitectures mini colloquium. So now if those who are still around want to turn on the camera, we can take a picture for this second day and then stick it